Okay, so I think we should be live. Hello, everybody. Thanks for tuning in. This is I think the fifth stream, something like that. And I have to apologize, like I didn't do any streams last weekend and the one before. Basically, due to a multitude of factors. Like for once, here in Berlin, it's absolutely brutal. Like it's so hot that it's kind of hard to take. Like this weekend, is a bit better, but I've been kind of slow generally, and then also I have a couple kind of new projects going on that I hate doing. I hate talking about it this way, but I can't really say much about those. But there's a bit of stuff going on that I'm working on, and this is kind of eating up a lot of time, and so I had to cut back a bit on the streams. But still, I thought, let's kind of get back into it. And the reason why that kind of fit is actually because I am currently working on the next episode, which will be on a VCA. And if you've been following the channel, maybe you saw one of my previous streams where I also built VCAs, but the main one we built there actually was using diodes, so it didn't use transistors. And that is, if I'm being completely honest, it's mostly just because I am very bad at working with transistors. And this is kind of what I heard from you guys. Like many of you guys kind of tell me that they have a lot of trouble with transistors. Like they say, oh, transistors are kind of like a black box, like they're a mystery. Like I don't really know what they do, how they do it. I don't know how to set them up, all this kind of stuff. And like I said, I have to kind of agree there because, I did use transistors in some of my designs, but generally it's kind of mostly just copy pasting. For example, if I need an amplifier, of course, I can look it up. I can find a schematic for an amplifier. I can plop it into my circuit. But to be completely honest, like I never really understood exactly what was going on. And so I was kind of trying to force myself to look more into transistors by choosing this transistor-based VCA for my next video. And this kind of pushes me into the direction where I need to look stuff up and understand stuff and so on. And like I'm already I've designed the VCA, it's working, but I'm still like in the phase of where I'm writing the script. And the problem there is always that I really want to be sure that I explain it in a way that not anyone, but people who are interested in this topic can understand. So that's always my goal. And when I write the script, I want to be as specific, as precise, but also as simple as possible. And this is also what this kind of stream, I hope what this kind of stream will do for me, because it will force me now to kind of reflect on the stuff that I've read and the stuff that I've tried, and kind of explain it in detail to you guys. And I think this will help me also to continue writing the script. Okay, that being said also, I used to say this in my videos, let me just reiterate this. I am not an engineer, I'm not an expert, like I am just a DIYer like you, like sitting at home, trying stuff, figuring stuff out, and then telling you about it. So it is always possible, if not likely, that what I'm talking about here may be imprecise, maybe a bit off. So just take stuff that I say with a grain of salt. But still, I'm quite confident in kind of what I discovered. So I'd say let's dive into it. So my approach for this stream is actually maybe a bit strange, because normally, and I guess you already did, you also did this before, like when you go on YouTube and you look for tutorials on transistors. You type in, I don't know, like NPN transistor tutorial, you find a video, and what they usually do is they explain what the transistor is. So, like they explain all the features, like, which terminal is which, what they do, and then they set up a circuit, and then they show you what it is. And for me, most of those videos didn't really work, so I didn't take much away from that. So I was kind of thinking, why not go with a kind of different approach? So my approach is, I don't want to describe what the transistor is, but instead I want to describe what the transistor is not. Okay, and one thing I need to make clear, I think, is when I'm saying transistor here, I am referring to BJTs, so bipolar junction transistors, which would be NPN transistors and PNP transistors. You know, so just so you know, I'm not talking about MOSFETs here. I'm also not talking about JFETs here. So I'm only talking about BJTs, and that's because to me, from what I see in the DIY scene, the BJTs are much more widespread. They're used much more than MOSFETs and JFETs. And I'm not saying that, you know, MOSFETs, JFETs don't have any value. Like, I think they are very interesting. I just don't know much about them, and I want to start simple and kind of from just the time I spend researching stuff. BJTs are what I put the most time in, so I think it makes sense. I think it makes sense to start there. So, you know, just for this stream, every time I say transistor, I mean BJT transistor. Okay. With that out of the way, let's go back to this, what I explained before. I want to look at what a transistor is not. Like, now this might sound a bit strange. Like, why would I choose that approach? And it's actually quite simple. Again, like, I have received a lot of like messages, comments, people asking me about something very specific, and that is, hey, is there any component or any compact little nice circuit that I can use to replace a potentiometer so that I have voltage control over a parameter? So the kind of hope here is often, you know, that you have a device, something like a transistor or something else, doesn't matter, that you can basically insert into any circuit, like where there's a potentiometer, and then you can just control it just by plugging in a voltage. And I have to disappoint you, or I always have to disappoint people when they write me because of this, because it's not that it doesn't exist, like it just doesn't exist in an ideal form. So it doesn't exist as a compact, small, cheap, easy to use component. So there are like a few things that kind of come close. So for example, Vectorals. Vectorals are actually kind of very close to a voltage controlled resistor, but they have like their own problems, you know, because they are not reliable. They have like slow reaction times, so that they're not ideal. And then also what you can do is you can use OTAs, you can use operational transconductance amplifiers. But, you know, I think if you want to implement a proper voltage controlled resistor, you have to use two of those. You have to set them up in a specific way. And then you get kind of a VCR, but the problem is that, you know, OTAs are expensive compared to other chips. Also, I said this in the last stream, I think they are going to be discontinued in the through-hole format. So in the future, I think you will only be able to get them in the SMD format. And this means that probably they're going to be harder to get at some point, and maybe at some point completely die out if no one else picks it up. But yeah, that's what I usually tell people when they ask me for this. But to put that aside, I'm still like, this idea has always intrigued me, like of a voltage controlled resistor. And when I was starting out building my stuff, I was, like many of you, I was actually looking for that kind of component. I thought like, hey, maybe it exists somewhere. And then once I came across transistors for the first time, I thought, hey, isn't this a voltage controlled resistor? Like to my naive mind, this was exactly what I was looking for, right? And the interesting part is, and that's why I did this little intro where I told you that you shouldn't take everything for granted that I say. Like if you think back to my VCO videos, then you'll maybe remember that in those VCO videos, I actually claimed that we are using such an NPN transistor as a voltage-controlled resistor. And I got some comments of people saying, like, oh, I didn't know that you can use them as a voltage-controlled resistor, and they seemed very happy. And I assume that then they tried to use that new knowledge in some circuits, and they were severely disappointed because, spoiler alert, a transistor is not a voltage-controlled resistor, not at all. And this is actually what I want to compare it against, because, you know, maybe, like, my hope is that maybe for you it's like the same, you have the same fantasy, you would also like to have this kind of device. And so my approach here will be, we will try to find out why a transistor is not a voltage-controlled resistor. That's kind of the premise here. Okay. So how do we go about this? Well, I think the first thing we would need to do to kind of make this make sense is we need to talk about resistors, about boring old resistors. And there are basically three main properties that I would want to focus on here when we're talking about resistors. And to kind of illustrate that, I'm going to now switch over to the circuit simulator. And since I always get a lot of questions about the simulator, let's just put the disclaimer right away. So this is a circuit simulator, and it's called Circuit.js. And the page that you can access it on is called Felstat. So you can either just take this link and go to the page, or you can also Google it. Like if you Google Felstat and circuit simulator, you should find this page. Okay, so with that out of the way, let's talk about resistors. So what I'm going to do is I'm going to kind of prepare like the simplest circuit here ever, which is literally just going to be a resistor. I mean, the value doesn't really matter, but let's pick a 10K. We have a 5 volts power source up here, or voltage source, sorry. And I will apply ground. I will apply ground down here. Oh, and one thing, I am aware that you can't see my cursor. I tried to fix this, but it's not elegantly solvable, or I didn't find a good solution. So what I try to do is, whenever I show something on here, I will like draw one of these rectangles to kind of show you, to highlight something. Okay, so right now the simulator is not running, so you don't see anything. But if I reset this and then I run the simulation, maybe turn on the current speed a bit, and this is a fun feature. Like with this dial, you can kind of adjust like how extreme the visualization is. So you can see, like in the bottom right corner, you can see that we have 500 microamps going through the resistor. And by dialing this up or down, we can kind of change the representation. So if I put it to the maximum level, it's still 500 microamps going through the circuit, but now it looks just much faster. So it's just emphasizing the speed of the current. That's what that is doing. It's very simple. Okay, and what I want to show you is, I mean, this is very trivial, but as you can see, there is a current going through our resistor, right? Because we have a voltage source here, and we have a ground connection here. So we have 5 volts between this point and this point, and because these 2 points are connected with a resistor, we see a current flowing through the resistor. And as we saw before, if I hover over here in the bottom right corner, you can see that we have 500 milliamps flowing through the resistor, right? Okay. Now, if I can put this in the scope, and what I can do is I can take the voltage away, and now all we see here is the current. So this yellow line down here that you can see is the amount of current that is flowing through the resistor at this moment. Okay. Okay, so now what I want to do is I want to describe to you 3 properties of a resistor, and like these are all 3 that I could think of. And if there's any more, then please put it in the comments if I missed something. But yeah, these are the 3 properties that I would want to talk about. The first one is linearity. The second one is symmetry. And the third one, I can't really, like, it's a bit awkward to talk about it. I think, like, can't put it into an adjective. Like, a resistor is floating. I guess this will make sense later on. So for now, just take it as I say it. And I think that the first 2 attributes are more important anyway. Okay, so let's first talk about linearity. What do I mean by linearity? Well, it's a very, very simple rule. So obviously there is a relationship between the voltage up here and the amount of current that is flowing through the resistor, right? So as I said before, right now we see 500 microamps going through the resistor. Now, what happens if I increase the voltage here? Let's say we jump from 5 to 10 volts. Surprise, we have more current going through our resistor. So now we are at 1 milliamp. And you might notice something. If I go back down to 5 volts, then we are at 500 microamps. And coincidentally, 500 microamps is exactly half of 1 milliamp. So from this, we can deduct like a very simple rule, which is whenever we double the voltage, the amount of current going through a resistor also doubles, right? So now we have 1 milliamp, and if we cut the voltage in half, we also cut the current in half. So now it's only 500 microamps. Okay, and this is true like all across the spectrum. So even if I go like extremely crazy and I put like 1 kilovolt up here, which is a bad idea, don't do this, you will fry your resistor. Also, where would you get 1 kilovolt? I don't know. But you can see that we now have, 100 milliamps going through the resistor. And if I go ahead and do something really crazy and I double it again, so I go up to 2 kilovolts, then we should see the current double again. And that is exactly what is happening. So now we have 200 milliamps going through the resistor. So, and also I can. Oh no, that's actually the next point. But yeah, I hope this is clear. So for a resistor, there's like this rule that that I call linearity. It's for a given increase in voltage, you will always see a proportional increase in current going through the resistor. That's just how they are. That's just what they do. So this is one thing that our voltage controlled resistor would need to kind of fulfill or do for it to kind of work in our circuits, right? Okay, the next point is symmetry. So what do I mean by symmetry? It's actually very easy. So let's say we don't apply a positive voltage here, but rather a negative voltage. So let's say we go down to minus 5 volts. And the question is, what will happen? You might have guessed it. And as you can see, our current is now coming from ground and is going towards the voltage source. Because, I hope you all know this, ground means nothing more than 0 volts. So if this is 0 and this is minus 5, then obviously the voltage here is lower than the voltage here. The voltage difference between these 2 points is 5 volts. And so we have to have a current flowing from down here to up there. I hope that makes sense. Okay, and now if we look at how much current is flowing, we can see that it's 500 microamps. But the thing is that they're flowing in the other direction, right? So now they're flowing. They're flowing from ground and into our voltage source, basically. But it's still 500 microamps, just like it were when we had 5 volts up here, and it was flowing in this direction, right? So right now it's also 500 microamps. And that's what I mean by symmetry. So it doesn't matter if the current is going in this direction or it's going in this direction, you have the same, like the resistor will behave the same way. And again, if we double the negative, no, not double, is it half? No, it's not half. Well, I guess you could say you double the negative voltage, even though that sounds really awkward. But yeah, let's double the negative voltage and let's go down to minus 10 volts. And then again, we can see that still the linearity holds and we get 1 milliamp. So again, double of what we had before. Okay, so that's rule number 2, proven. And the third rule sadly doesn't really apply. So what I mean with floating is kind of like for a single resistor that is not controlled with a voltage, it doesn't mean much. So it's something that we will need to have a look at once we're talking about the transistor in the end. So for now, I would say just leave it by the wayside, ignore it. We will come back to that later. And I will switch back to my desk and I will look at the chat for a second to see if someone had a question. So, oh, you can use the mouse scroll wheel when the mouse is over the resistor to increase, decrease the resistance value. I could do that if I had a mouse. I'm on a trackpad. I'm not sure if there is a alternative there. Okay, and Mike says, this confuses me. I always turn conventional current off in the options. Yeah, one thing I got, like yesterday I got a comment again, and I used to get a lot of comments of people asking me, like, why do I use the conventional current flow? So for everyone who does not know, there are basically 2 different ways of looking at a circuit. And the first one would be that of the conventional current flow, which assumes that electricity is flowing from positive to negative terminal, right? So if you have, let's say you have this battery here, and you have a positive terminal and you have a negative terminal, and now let's assume, or we don't even have to assume, like I will just take this resistor and I will waste energy and I will hold this to the terminals. Then what will happen is, in the conventional model, what would happen is that the electricity is flowing from the positive to the negative pole through the resistor. But it turns out this is wrong. I find this very funny, actually, that people just messed it up so thoroughly. So people used to think that it's this way, but it's not. It's actually the other way around. So electricity is flowing from negative to the positive terminal. And this is unfortunate, to say the least. But I think for a different reason than most people, or I think it's for different reasons than most people think. And that is because. Wait, let me switch back to the simulator, then I can show it better, I guess. Boom. So I think it is unfortunate because of a very simple reason. Let's say we take a diode, right? So, boom, diode. And as you can see, it has an arrow and it has a line. And this, like I'm pretty sure there's also the official way to look at it, but to me, this obviously signifies that electricity can only flow from here to here, like in the direction of the arrow. And the line to me implies that current is blocked from flowing in this direction, right? So this makes sense. There's a line here, so it's blocking, and there's an arrow here, so it's allowing current to flow. And this actually aligns with the conventional model. So if I now take a voltage source here, and I should probably dial it down because we don't want the simulation to crash. I put it here, and you can see that in the conventional model, like where electricity is flowing from positive to negative, it is flowing in the direction that is kind of indicated on the diode symbol. And my problem with the kind of correct, like with the I don't know what the actual term is, like with the physical model, like with a real model, is simply that it's really confusing to beginners. Like I saw like a bunch of tutorials on YouTube where people like they are trying to teach the absolute basics. They're trying to teach the absolute basics to people who have no clue. And they start off by first explaining the conventional current flow. Then they explain the actual current flow. And then they start working, but of course, they use these symbols. So then what happens, at least in my experience, is that newbies get completely confused for no good reason. Because the thing is that it turns out in the end, I don't know if there's like some cases where that's not true, but in all cases that I've encountered, it doesn't matter which model you use. Like it doesn't matter if you say that electricity is flowing from positive to negative or in the other direction. It's completely irrelevant for how you analyze your circuits. And that is why I think, or that is why I actively only kind of teach, and I don't mention the real model. Like I just actively teach the conventional flow simply because it may be wrong, but it works, and all the symbols are kind of tailored to the conventional current flow. And so my goal is always to make it as easy as possible for people to understand. And that's why I use the conventional model, because I feel like it's just less confusing, and people gain nothing from knowing that it's actually the other way around. So that's my reason for that. Okay, with that being said, let's get back to it. Hope that wasn't too much of a rant. Let me check the comments. I like to use the way that makes sense, the line blocks. Yes, it's more comfortable to say that electricity flows from positive to negative. Yup. Okay. Christian asks, is the same amount of current flowing through every resistor? You mean if there's differences between different 10K resistors? They are not exactly going to be 10Ks. Like they're going to be, like when you buy a pack of resistors, they will have kind of specification. They will say what the tolerance rating is. So these, for example, are 1%. So they are going to be off. They are not going to be exactly 68K, like they claim on the label here, but instead they will be off. But if they have the exact same resistance value, you will have the exact same current going through them, given that the voltage is the same. Okay, so let's get on with this. In the end, we want to talk about transistors, right? So, yes. So I just showed you what this resistor does, how it works, and what we need to expect from a voltage-controlled version, right? So, what I've drawn up here is kind of a wish list. This is kind of what I wished for when I was beginning. Yeah, a component that would kind of make it much easier to design my circuits, and that would be a voltage-controlled resistor, or VCR for short. And yes, it's kind of unfortunate that a VCR also plays movies, but let's just go with this abbreviation, I think. And yeah, okay, so it's a bit chaotic, but let me explain. So you will find the three properties that I just talked about in this ideal model. So first of all, linearity. So let's assume we take these terminals away. Then this would just be a regular resistor, right? So we have a terminal here, we have a terminal here, and this is an input, also an output, and this is another input/output, right? And what we would expect to happen is that if we increase the voltage at this point linearly, so we double the voltage, for example, then the current going through the device should also double, right? So that's what a device like this should ideally be able to do. Then also, what's important is that this device should be symmetrical. So it should work in this direction. So the current should be able to flow this way, but the current should also be able to flow this way. It's kind of the second rule. And now the third thing with the floating stuff that I talked about earlier, this is kind of tied to these other two inputs. And now you might ask, why do you have a CV input here and also a ground connection? Wouldn't it be enough to just have a CV input, right? And the answer to that is, well, no. So the problem is that, and I talk about this a lot, the problem with voltages is that voltages are always relative. So let's say, I took my power supply and I gave you this cable, which is connected to the positive terminal of my power supply. And let's say it's a variable power supply, so I dial in any voltage and I don't tell you what voltage it is. Just with this cable, you will not be able to tell me what the voltages are dialed in. To be able to tell me, you need the other cable, the one that connects to the ground connector on the power supply, right? Because voltages always describe a difference in potential. So it's always kind of a relation, right? So let's say I've set the power supply to 12 volts. Then the way you measure this is you take your multimeter, you put the positive probe to this one, you put your negative probe to this one, and then what the multimeter basically does is it looks at the difference between these two terminals, and then it tells you, hey, it's 12 volts. But if you just give it this, it won't be able to tell you. So this means that in order for our mystery device here to be able to know what kind of control voltage you put in, it needs to have a ground reference. So it needs to know where is 0 volts, where are we in relation to that, and then it can kind of do its thing. And I realize that it's a bit abstract, but yeah, that's the point here. And then kind of tied to that, or not tied to that, however you want to see this, is, and this is the last point, is that the CV input needs to be kind of decoupled from this terminal and also from this terminal. So what do I mean by that? Well, the voltage here at this point should not interact with the voltage here or the voltage here in any way. So if the voltage here rises, the overall resistance of the device should be at the same level. Let's say I put in 1 volt here, and we expect that the resistance of the device is now at, let's say, 1 kilo ohm. Then we want this to be stable regardless of what the voltages at these points are, right? So that's kind of the last thing. That's, I think, what's generally referred to as a device being floating voltage controlled resistor, where it doesn't matter what the value is here, basically. Okay, so now we have kind of described what the ideal situation here would be. And with this in mind, we will now go into the simulator again, and we will look at an actual or a simulated transistor, and we will put all these things to the test. Because maybe I should do that, because the transistor is kind of close to this, because it has this kind of in-output terminal 1, which you could call the collector of the transistor. It has like the second terminal, which you could call the emitter. And then it has like this third terminal, which you could call the CV in. Now, if you are, if you took in what I said, then you will already say, wait, but the transistor doesn't have the ground reference, right? It doesn't have the fourth connector. A transistor only has 3 connectors. So how could this be our ideal VCR? Well, let's check this out, and let's find out why it does not work. So I will switch to the simulator again, and I will get rid of all of this stuff. Okay, so first of all, we will take our transistor. Boom. So this is an NPN transistor. You can kind of identify this by this little arrow that is pointing down or pointing outwards here from the base. A PNP transistor, on the other hand, as you might know, will look like, like this, where you have the little arrow pointing inwards toward the base. And we are not going to talk about the PNP for now, maybe later. For now, we are going to focus on the NPN transistor, which is this one. And again, like I said before, we have these three terminals. So we have the collector, which is the terminal up here. We have the emitter, which is the terminal down here. And we have the base, which is the terminal right here. And now, with our naive approach, with what I just said, we could think, or we would think, and I used to think, that maybe like between the collector and the emitter, we basically have a resistance that is controlled by the voltage that is applied to the base. This is how I thought it works, right? So let's put this to the test. Let's see if that is actually true. So the first experiment that we're going to do is we're going to build a very, very simple little circuit. So we are going to put a voltage source at the collector. We are going to connect the emitter to ground. Oops. I think I would rather leave a bit more room here. So I'll do it like this. Boom. And then we also need a little more room up here. Okay. And then what I will do is I will take a voltage source. I'll put this here. I will put a relatively low voltage here, which we will get to. Like we will get to why I chose 500 millivolts for this in a second. But for now, let's just assume that I know what I'm doing, and let's just assume that this is kind of correct. Okay, so what I will do now is I will run the simulation. I will turn up the current speed so that we can see what is happening. Okay, and as you can see, hopefully I can zoom in a bit, maybe that helps. What you can see is that we have a steady current going through our transistor, right? So if I hover over this in the bottom right corner, you can see that there's a bunch of parameters, but most of them we actually don't have to care about. So what we do have to care about is the value IC for the moment. So that's the one at the top. So you can see that IC is equal to 24, let's just round it up and say it's 25 microamps. Okay, so if we compare this to our previous circuit with the resistors, and we can actually just do this in here, basically. So let's just take a resistor, and of course I know what the proper dimension is, like I tried this before, so you know, I didn't pick this by accident, but yeah, what we can do is we can put this in parallel, basically. So now we have, I mean, just to make it more clear, I mean, to make it maybe a little bit less confusing, we could do it like this. It's the same thing, but I think it might be a little less confusing, because now we have two separate circuits, right? We have the circuit with the transistor, and we have the circuit with the resistor. Okay, and as you can probably see already from the visuals here, again, the transistor, we have 25 microamps going through it. And if we look at the resistor, we can see that we have 25 microamps going through it, right? So at a first glance, this looks like maybe it actually works as a voltage controlled resistor, because now we can try and see what happens if we decrease the amount of voltage that we apply to the base. So right now we're at 500 millivolts. Now what we can do is we can drop it down to 450 millivolts, right? And we can immediately see that something is happening. So we can immediately see that the amount of current has like really reduced. And now we're at 3.5 microamps. And if we wanted to have the same result here on this side, we would need to bump the resistance value up considerably. Like, I'm not entirely sure how much it's supposed to be. Yeah, that's close. So with a 1 mega ohm resistor, we have 5 microamps going through it. On this side, we have 3.5. So we would need to raise it up even more. Let's do 1.5 M. And yeah, that's close. So, well, what we saw is that by decreasing the voltage we apply to the base, we are significantly decreasing the amount of current that is going through our resistor, right? And now our transistor kind of behaves like a 1.5 mega ohm resistor. And so this might sound confusing to you, because now, you might ask, okay, so actually it works, no? So we changed the voltage here, and apparently we changed the resistance on this path. Yes and absolutely no. So let's go back to the situation from before. So we apply 500 millivolts to the base here, and we drop this guy down to 200K. And now again, we can see that here we are close to 25 microamps, and on this side we have 25 microamps exactly. Now what I'm going to do is I am going to change the voltage up here. Because remember what we saw with the resistor, and I will show you again. If I double the voltage, then we get double the amount of current that will flow through the resistor. So now we're at 50 microamps, right? So it makes sense. Double the voltage, double the current. Now, we would expect that the same thing is true for the transistor. But if I bump it up to 10 volts, whoops, then we see that nothing happens. We are still at about 25 microamps. And weirdly, it completely doesn't phase the transistor at all if I increase it. I can even bump it up to as far as like 1 kilovolt. And probably this is not a good idea to do this in real life, but you can see we are still at roughly 25 microamps, which is very strange, because if I if I do the same thing to the resistor, then we are at 5 milliamps already. So this is orders of magnitude more. But the transistor just doesn't care. It just, it doesn't matter. And also, we can drop it below 5 volts. So let's say we go down to 2.5 volts. And we still have 25 microamps going through our damn transistor. And we can drop it even more. We can drop it to 1 volt. And we still have 25 microamps going through our transistor. Now from here on out, things get a bit weird. Like once we drop to below the base voltage. So let's say we go down to 250 millivolts. We can go down even more. Let's just go down to 50 millivolts. So weird things are happening here. You can see that more current is going into the base. And you can also see that we are dropping down to 17 microamps. And you can also see that in the bottom right corner it says saturation. So we will talk about this in a bit. But for now, just know that what I just showed you, so this kind of independence of the current going through the transistor in regards to the collector voltage, only is true as long as we are above the base voltage. So if I go up again to 600 millivolts, which is above the base voltage, because 0.6 and we have 0.5 here, you can see that we are again at 25 microamps going through our transistor. So let's keep this in mind for now. Like this only works as long as the collector voltage is above the base voltage. Okay, so why did I show you this? Simple, because it already disproves. Or it kind of shows us that the first thing, the first requirement for our ideal VCR is not fulfilled. It doesn't work, because remember, we said that for a voltage-controlled resistor to be an actual voltage-controlled resistor, we need to have this linear relation between the input voltage and the current going through the device. So already our transistor is not living up to the requirements. It doesn't work. You know, this, no, it doesn't work. Okay, but it gets worse. So let me check back into the simulation. Okay, so we said that we need to be able to reverse the direction of the current. Whoops, that's not correct. We need to be able to reverse the direction of the current, and it should still behave the same way. So here you can see with a resistor, we still have 25 microamps going through it, right? Now let's try the same thing with our transistor. So again, just to check, at 5 volts, we had our 25 microamps going through the resistor. Now let's drop this to -5 volts. And we can already see that there is a problem, but this is something that I want to get to in a second. Okay, so to get around this, what I'm going to do is, instead of inverting the voltage here, I will simply turn the transistor on its head, basically. So I will exchange the collector and emitter terminals. And we can do that by ticking this box. Okay, so now the emitter is where the collector was, and the collector is where the emitter was. And so now the current is going through the transistor in the opposite direction. So it's comparable to what's happening here, you know. Okay, and what I want to show you is, remember, like before, in the same situation, with the same 5 volts here, with the same 500 millivolts here, we had 25 microamps going through a transistor. And now it says we have -49.7, so let's just say -50. Why does it say minus? Well, because the simulation software basically, like for the simulation, the normal direction would be from collector to emitter. Right now, the electricity is flowing from emitter to collector, and so the simulation puts a minus in front of the current. But we don't really have to care for that. So we can just say, okay, so we have 50 microamps going through our transistor. Swap it back, and we can see we're at 25. And if I swap it back, we can see we are at 50. And I can't give you the specifics of why this is the way it is. I just read that kind of the transistors are made this way. So they are made in the way that they kind of, I don't know what the correct word is, like they expect the current to go from collector to emitter. And that is why they are asymmetrical. And that is our second thing that we don't have for this to be a voltage controlled resistor. So it's not symmetrical. It doesn't behave the same way in both directions. So it matters in which direction the current goes. So second thing that's problematic, right? And then there is a third thing that is problematic, and that concerns what I said about the device, like that it should be floating. So I hope you will kind of see what I mean by that in a second. So if we take the ground connections out here, so up until now we had, like we used ground, so 0 volts as a kind of negative voltage down here. And now what I will do is I will, instead of 0 volts, I will pick like a very small positive voltage. So we will say 50 millivolts, so 0.05 volts. And we will try to have a look at what this does. So here again, so as long as this was sitting at 0 volts, we can do this again. We had the same current going through our resistor and through our transistor. So in both cases, it was like 25 microamps, right? Now, if we go in here, and as I did before, we bump this up to 50 millivolts, we can something weird happening. So all of a sudden, the the current going through a resistor dropped as we expected, but it didn't drop by much because I didn't raise the voltage here that much. So between these 2 points, we still have 4.95 volts from here to here. Whoops. Right, and that's why the current going through here like barely decreased. So instead of 25 microamps, we now have 24.75, right? But for our transistor, we are already at 3.5 microamps, okay? So again, at 0, it was 25 microamps, and at 50 millivolts, we are already down by like 20 microamps. So it's a huge amount less. And then if we bump it up even more, so let's say we go up to 100 microvolts on both sides, again, predictably, the resistor, like the current decreases a little bit, but it's still 24.5. The transistor, on the other hand, is now in the nanoamps. So there's barely anything going through the transistor. And this is what I meant when I said earlier that for our ideal voltage-controlled resistor, the relation between the base voltage, or there should not be a relation between the base voltage and any of these two voltages. And curiously, these two, like the collector voltage and the base voltage, they are actually decoupled. As we saw earlier, like if we change this voltage here, it doesn't matter. Like as long as we stay above the base voltage, it's fine. Like we have the same current going through here. But obviously, if we change the emitter voltage, then immediately the whole device acts completely differently. So we can also go in the opposite direction. So if we go in the negative direction, then we can see that it's increasing massively. So now we're at 1 milliamp going through the transistor. That's really a lot more current. And I mean, you can see like in the simulation, like it's going absolutely crazy. So that's our third problem. So, and this kind of harkens back to what I said earlier. If we look at the sheet again, what I said earlier is that the CV input needs to be decoupled from our two in and output terminals, right? So that the voltage you apply here only influences the resistance and it does not interact with these voltages. But in reality, with our transistor, the base seems to be like directly coupled to the emitter. So the voltage at the emitter very much matters because it seems to be in some kind of relation to the base voltage. So that's kind of strike 3. So that's the third reason why this thing doesn't work as a voltage-controlled resistor. Okay, weird. Then the question needs to be asked, why did I, like in that VCO video, why did I say that I'm using a transistor as a voltage-controlled resistor, and why was I able to replace a resistor with a transistor? Well, to answer this, let's go back to the original VCO design. So actually, we don't need to care about any of this stuff. This is all irrelevant. All we need to care about is this oscillator core here. Okay, so I hope you kind of remember like how it worked. I can explain it just really quickly. So at the center of it all, we have this Schmidt trigger inverter, and the Schmidt trigger inverter basically always looks at the voltage at this point. And if the voltage at this point is below a certain threshold, so if the voltage here is low, basically, then the Schmidt trigger inverter will turn its output on, which will cause a current to flow through the diode and into the capacitor, and it will fill up the capacitor. And as the capacitor fills up, the voltage at this point gets raised, because I like to use this kind of water analogy. The capacitor is basically like a balloon that you push water into, and at first you can push water into it easily because the balloon is empty, but as the balloon kind of like fills up, it kind of pushes back, and that raises the voltage here. And as soon as the voltage here goes past a certain upper threshold, the Schmidt trigger inverter will turn its output off, right? So there's no current coming from here. The capacitor is filled, and that means when this is off, that there is no force pushing kind of into the capacitor. So now the capacitor is kind of able to push its contents back into the system. Okay, and then the question is, where does the content of the capacitor go? So, and it can't go into the Schmidt-Trigger inverter because this is not, like no current can flow in here. Basically, this is a diode, so it doesn't allow for anything to flow through here. And so the only way that is there, besides this, but you know, this is also not a current input, so nothing can flow in here. So the only way that the charge can go is through the transistor here. And what I did initially, like in the video, like how I explained this was I used a resistor here instead of this transistor. So I had just I don't know, like 100K resistor connecting these 2 points basically. And now the question basically is why was that possible? And to answer that, we will go back to the simulation. And I hope that will make it a little bit more clear, and that might also clear up how the resistor actually works. So what we will do is we will connect this back to ground. And now I will just basically replicate the oscillator circuit. And I guess some of you already know that this is a kind of tricky endeavor because unfortunately the simulator software is not very fond of this oscillator core that I was just talking about. So and I can just show you quickly. So if I just exactly replicate what you just saw, on the schematic, which is, I put the diode here. You always, like if you use this, always make sure that you are using, that you are selecting the proper diode model. Because if you want to be modeling this switching type diode, which I mainly use, this model behaves very differently from the default model. So the default model will give you all kinds of strange behavior. So always make sure that you are selecting the switching diode model if you're using this. Okay, so we do this. And then we also put the capacitor here. And let's really follow the schematic. So at first I will put a resistor here, and I will dimension it. I will put quite a big resistor. Okay, so I'll connect this here, and I'll connect this here, and boom. So unfortunately, this software is kind of confused when it comes to this construction, and it always tells you convergence failed, which is very unfortunate. Thankfully, there is like a kind of ham-fisted way to get around this, which is you need to put a resistance between the diode and the capacitor and resistor. And I have to now test like how big it needs to be. Let's see. Okay, this still fails. I think something that also helps is increasing the capacitor size. I think maybe. Yes. Okay. So now, since we want to be able to see the signal at the output, I'm going to put an output here. And yes, there we have our nice oscillation. We bump up this resistance here. And yeah, it's not ideal with this resistor here, but it works for now. Okay. So if you have a very keen eye, then you might already notice something strange about the shape of these sawtooth waves down here. You might notice that the back, like this descending, the descending curve, like from the peak level to the valley level, you might see that it is curved, right? So it curves. You can see that in the beginning, it starts off steeper and then it slowly curves. And the question is, what is up with that? maybe I can make it more obvious. Like if I really exaggerate it, I can manipulate the values here for this Schmidt trigger inverter. So I will just bump this up massively. Let's put it up to 14, 16 volts. I don't know. Yeah, I think now it may be more obvious. Maybe it isn't more obvious. Maybe if I do the max scale thing. Yeah, I think now you should be able to see that it's bent. And the question is, why is it bent? And the answer is actually really simple. We already talked about it. So what you see here is the voltage at this point, right? I'm picking up the output from here, which is connected to this point. So it's like at the capacitor. So it's basically the voltage the capacitor sits at. Sorry. And so basically what happens is, once the Schmidt trigger inverter fires, it goes high, it charges up the capacitor. Right now it charges it up to 16 volts. And then what happens is that the Schmidt trigger inverter turns off, like we just talked about, right? So this is now at 0 volts, so there's no current coming from here. So the only route that the charge from the capacitor can take is through the resistor and to ground, right? Now here's the thing about resistors. As we said, there is a direct relationship between the current flowing through them and the voltage we apply to them. So this means if the voltage at this point is high, we are going to have more current going through this resistor than once the voltage here drops to this level, for example. So if I turn the speed up here a bit, you should be able to see this, right? So kind of try to see like whenever you get the peak here. So whenever the Schmidt trigger goes off, you can see that you have this sudden burst. So it goes very quickly and then it slows down. Until the end, it's very, very slow. And then boom, you get the next hit. And this is exactly what we actually expect from a resistor, right? Because like we said before, like if the voltage here goes down by half, then the current going through the resistor also goes down by half. And so the speed of the discharging process slows down. And also the voltage here will drop slower because the discharging takes longer. And that's how we get this little bend shape in our waveform. Which, I mean, of course, like in the video, I just did this for demonstrative purposes, and there it's completely fine. Like we don't care. We just want to see and hear it oscillate. But like if this was our actual oscillator, it would not be ideal. And the cool thing is, the question that I was asking going in was, okay, so if our transistor is not a voltage controlled resistor, then what is it good for? And the answer is exactly for this situation, because, keep in mind like how curved this is. So what I will do now, I will take this resistor, I will throw it away, and instead I will put our transistor here. And then you watch what happens. We get a beautifully straight line. Now the question is, why do we get this beautifully straight line? Well, we already talked about it. The thing is that if I hover my mouse over here again, and you look at the IC, at the current going through or into the collector, basically, you can see that it sits at our steady value, which is about 25 microamps. So it doesn't change. And the cool thing is, it doesn't change, not even if the voltage at this point here goes really high. So we can see the peak now is at 15 volts, and it goes down to just 4 volts. And the cool thing is, we always have 25 microamps going through our transistor. So this means that the discharging process, like the speed at which our capacitor is discharging, is always going to be the same. And that's why we get this lovely straight curve, which is perfect. And coincidentally, this is basically, and I think put this in the description, so this is the first checkpoint kind of. So what we have here is, I I don't know if that's actually the correct term, but I call it a current sink. And it's a constant current sink because, as we can see, it sinks always the same amount of current, and it doesn't care what the voltage here is. So this is one of the major kind of applications in which we can use a transistor in our synth circuits. So we can use it wherever we have this kind of situation where the emitter is connected to ground, so it sits at 0 volts always, where the base can be varied by us. So, in our case here, let's say we bump up the base voltage, we go up to 550. We can see that now, of course, the amount of current that is flowing through our transistor is massively increased. So our capacitor discharges much quicker, and so the frequency of our oscillation is increased. On the other side of the spectrum, if we decrease the voltage, then we can see that, that the speed of our oscillation is severely slowed down, right? So now it's really, really slow. And this is, in the end, what we utilize in the VCO design. So we basically just take our CV, our input voltage that we get, we scale it down to be in this area, like between, I think it's like between 0.2 volts and something like 550 millivolts, so 0.55 volts. And this way we can control the frequency of our oscillation quite reliably. And of course, but we'll get to that again in a minute, also the relation between the voltage we apply here and the amount of current going through the transistor is exponential. Like, this is really important, because otherwise we couldn't make music with this, because I don't want to get into it too much now, but like in music, the relation between notes and frequencies is basically exponential. So if you take an A at 440 hertz, for example, then the next A, so one octave up, would be at 880 hertz. So it's double that. And then the next A is again double that at 1760 hertz, something like that. So, so steps on the musical scale are exponential, and that's why that is important here. But we will get back to that in a minute. So I think right now the best course would be to actually do what I said in the beginning that I don't want to do, but I think now you maybe have enough context for this to make sense. So now I would kind of like to positively identify all the characteristics. No, what's the word? Let's go with characteristics of the transistor. So let's tear this down. Oh no, maybe I will go to the chat first, and I will see if you have some questions. My ideal VCR can also play Betamax tapes. Good one. Let's just remove the middle leg of the transistor and create some oscillators. Look, Mom, no computer star. Yeah, I'd say that's abuse, but of course you can do that. Martin says, I'd suggest to add a base resistor. Transistors are current amplifiers, no voltage. We will get to that in a minute. It's actually, it's more complicated than that. Like I used to also think like that, but it's kind of like you can't separate the two. Like you can't look at just current or at just voltage. So they are always interlinked. So you can't separate them, but we'll get to that in a second. Okay, Wilson says, that's because it understands the capacitor as ideal, meaning infinite current on a pulse. Yeah, that's pretty probable, but in effect, it just doesn't work. So it's just annoying. Yeah, cool. So let's go on. Christian, why don't we see the Schmidt trigger pushing into the capacitor in Feldstedt? I think because it's so quick, like it's extremely fast, like Wilson said, because it's like, I don't know, Wilson says it's infinite current. It's also infinitely fast, basically, because it's just instant. I think that's the reason. Grumpy L Sunshine says, try 1 or 10 ohms at the feedback path resistor. You mean in the oscillator? I don't like. I had to use a fairly big one for it to make sense, for it to work. So I don't know. What else? Why does such a small change in the base result in that? We will get to that in a minute. Thank you. I hope this is understandable. Okay, so I think we will just get back to it. So what we will do, like I said, I will get back into the simulation, and we will look at like the most fundamental things about the transistor, and I hope I can cover everything. Please put your questions in the comments, and I will try to answer them as best I can. Or if I don't know the answer, we just try it out. That's how I get most of my information anyway. So let's go like really slow. So what I will do is I will take a resistor. Yeah, Freudian slip. So I will take a transistor, and I will first, I will kind of dissect the transistor. So what we will do is we will completely ignore the collector, and we will only look at the base and at the emitter. And if I zoom in, it's probably unnecessary, but what you can see, I hope you can see, is, and I talked about this earlier, this little arrow. There's this little arrow that's pointing from the base towards the emitter. And actually, it's not a coincidence that it's an arrow. As you might remember, there is something else that also has an arrow in the symbol, which is a diode. So, like I said, it's no coincidence because this is just a diode. So between base and emitter, if we exclude the collector, this is just a diode. And it behaves like a diode. It behaves like a different type of diode, I would say. I mean, it's anyway like no diode kind of behaves like the other, so there's always going to be variation. But I'm just saying this because here in the simulation, like the way these two diodes basically are modeled differ a bit, but still I can prove to you that these are in essence both diodes. And the way that we will do this is we will do a very similar thing as what we did with the resistor, which is we will take just a voltage, and we will connect this side to ground. And whoops, someone called the ambulance. I will put a connector to ground here, and oh, it doesn't explode. That's interesting. I would have expected that the simulation crashes, because this is a lot of current. I mean, it's 6 amps already going through here. I actually don't know where the limit is with the simulation. I only know that at some point it kind of says nope, and it nopes out. Let's try to make it crash. 152 amps. Still going strong. 772 amps, and it's still going strong. Interesting. I thought it would crash earlier. 1.5 kilo amps. That's a lot of amps. But I mean, yeah, in the end it doesn't matter. But let's just go a bit easier here on the simulator. So I will send in 500 millivolts into this diode. And what we see is that we get 110 microamps going through it. And what I will then do is I will take another voltage source, and I will make it the same value. And yes, I know that I could connect it to the same source, but I just want to make it clear, because I think it might be confusing. If I connect the transistor to the same source, you might ask, like, oh, isn't the transistor eating up the current and leaving nothing for the diode? No, but just to make it clear, let's make this as 2 separate circuits. Okay, so I will put a connection to ground here, and what we can see is immediately that the current going through the transistor is less than the current going through a diode. And this is due to the fact, like I said, that the diodes are modeled differently. So here we can see we have 12 microamps going from base to emitter, and here we have 110 microamps going from, what's the word, cathode to anode? I'm not sure if that's the right term, but from top to bottom, let's say it like this. Okay, but how will I prove to you that this is also a diode? Well, simply by increasing the voltage. So I'm again, here we are at 500 millivolts. We have 110 microamps going through the diode. If I bump this up to 600, we go up to 831, which is a considerable bump upwards. And this is because, and I talked about this in my filter video, with diodes, it's actually there's actually an exponential relationship between the voltage applied and the current going through it. So again, with the resistors, it's a linear relationship. So I can show it to you. So for a resistor, if I would halve the voltage, we would see half the current going through it. But since this is a diode, that relationship is exponential. And I will make this more clear in a second, but you can see it's 1.9 microamps at 300 millivolts. And it is 831 microamps at 600 millivolts. So you can see it's definitely not linear. And now we will try the same thing with our transistor. And you can, I guess you can already see that the increase has been substantial. So now we're at 605 microamps. And again, if we halve it, we should be at, oh, it's just 5 nanoamps. So there's definitely something going on. Okay, and I think a better way to visualize this is actually the following. So we are not going to use a boring static voltage source, but instead we are going to use a waveform. And I like to use the, actually I think the sawtooth might work better. We will dimension it correctly. So let's say we do 250 millivolts with a 250 millivolts DC offset, and I will show you what that means. So I can put this here on the scope. And for now we are going to, because it's a spoiler, we're going to hide the current. So as you can see, what I dialed in here was 250 millivolts max voltage and 250 millivolts DC offset. And this simply means that we have a waveform that is going from 0 volts to 500 millivolts. That's what that means. So the center is at 250 millivolts here, right? And we will simply copy that basically. We'll take that and we'll apply that to our transistor. Sawtooth 250 millivolts max, 250 millivolts DC offset, and that might actually not be strong enough. I think we should bump this up just a little bit. So let's go 300 here, 300 here. So it's swinging between 0 and 600 millivolts. Okay, and what we can do now, you already saw this, is if I go into the plots and I can say, show me the current, please. And maybe I'm already doing max scale. That's kind of unfortunate. That is not very clear. No, we're going to take this out. And what we are instead going to do is we're going to put a piece of wire here. We are going to measure the current that is going through the wire, and we are going to do the same thing here. Boom. Show me in the scope, and we are going to hide the voltage. And I hope what you can see, maybe I will also just show you the original signal. I think this might be important to understand this. So let me hide the current on this side. Okay. We go max scale. We should probably go max scale here too. And here. Okay, so what we can see here is here in this oscilloscope, we can see the actual voltage curve of our signal. So it's a sawtooth signal. So it's going up and then it's rapidly going down, right? And maybe I should put a third thing here to kind of show you. I will take a resistor. So we take a resistor, we also take a piece of wire, and we take ground, and then we also look at this, and we also only look at the current. So what we can see here, hopefully, is kind of what we expect. Like for the resistor, since it's a linear device, we can see that the changes in voltage, which are in the shape of a sawtooth, they get a sawtooth kind of current response. So as the voltage rises, the current rises like linearly and proportionally. So, you know, higher voltage or doubling in voltage means doubling in current. So the shape is basically just reproduced, right? But with our diode first, like if we look at our diode first, we can see this is not the case. So instead we get this, like I don't have a better word for it, we get this exponential curve, right? So here we have this straight line, and here we get this curve. So in the beginning, the current is very low, and then as the voltage increases, it slowly gets stronger, and then boom, like it kind of explodes, and it's like kind of this exponential behavior. And we can see the same thing with the transistor, even though the characteristics are a bit different. Maybe, you know, it starts to go up later, and it stays low for longer. But just from the general idea of it, I would say that these two are of the same type. So we can definitely say that this is not a resistor. This is a diode, right? So here between base and emitter, we have a diode, which is kind of the first thing you should probably know about the transistor. But I mean, of course, it doesn't end there. Like this is not all the transistor is basically. And now it might get a bit complicated or a bit strange. I would say it's a bit strange. So what I will do now is I will take a voltage source and I will connect this to the collector. And as we can immediately see, I will just stop this here. Now we get way more current going through our transistor, right? So before the peaks were here, and now the peaks have already doubled. But if you look closely, the strange thing is that we barely have any current going into the base anymore. So if I take this out again, you can see that there's a bunch of current actually going into the base. I mean, it's like it's the only current that's going through a transistor right now. So, and you can see that it's actually moving and quite quickly also. But if I put, oops, okay, Control Z doesn't work. If I put the voltage source back in here, you can see that all of a sudden there is basically, there's a bit of current going in here, but it's not much, which is strange. And to make this more clear, I would say we go back to a steady voltage here. And this, yes, this is going to kill the simulation. So what we need to do is we need to drop this down. So, okay, so now let's talk about what we see here. And the handy thing about the simulator is that, again, if we, whoops, I didn't want to do that. If we hover over the transistor, we get all this kind of useful information in the top and the bottom right corner. So yes, we see what we saw before. We see the collector current, which right now sits at 25 microamps, like before. We also see the base current, which sits at 248 nanoamps. And then we see VBE, which is the voltage between base and emitter, which is 500 millivolts, as we know, like we can see here, 500 millivolts. Here we have 0 volts, and so the difference between the two is 500 millivolts, as it says there. Then VBC minus 4.5, we can forget about that for a second. VCE, 5 volts we know because, you know, we have 5 volts here, we have 0 volts here, so 5 volts difference. And then we also see the power, but the power is actually not that interesting for us. Okay, and now the question is, what is the relation, like what is going on here? Like what is the relation between all these numbers basically? And this might seem very overwhelming, but the core mechanic is actually extremely easy. And the core mechanic is kind of defined by another number that you can see in the bottom right corner that I didn't talk about yet. Like if you look into the first row, it says transistor, and then it says in brackets NPN, it says default, and then it says beta equals 100. And if I click on this, you can see that you can set this freely. So you can set any number in here. It's called either beta or HFE. And this might sound intimidating, but it's actually very simple. All this is the gain of the transistor. Now, before you kind of internalize this as something that you can rely upon, let me tell you, this is a very unreliable metric. So every transistor is going to have a different kind of amplification factor, so a different beta. So you should never rely on the fact that your transistor has a beta of 100. So I'm not saying here that any transistor has exactly a gain of 100. This is not true. This is a model. This is like a kind of ideal scenario. So this is not something that you should take as absolute. But just in the simulation, for this purpose, we can say that the gain of this transistor is 100. Now the question is, what does it mean? Like, what does it mean when the gain of the transistor is 100? And maybe you already saw this. You can actually find this in the numbers. If you look at IC and at IB, then you can see, or you might see, that IB is 248 nanoamps and IC is 24.8 microamps. And now, I mean, I'm not good at maths, so I'm not. It's not something that I excel at. But even I can see that the factor, the relation between IC and IB seems to be 100. So 100 times 248 nanoamps is 24.8 microamps. If I'm not completely mistaken, I will check in the chat to see if anyone objects. But yes, this is I'm pretty sure this is how it goes. And now we can kind of experiment with this. So let's say I decrease the voltage here. I go down to 450 millivolts. Then what we can see, if I hover my mouse over this again, we can see that now IB sits at 35.9 nanoamps and IC sits at 3.59 microamps, which interestingly, again, seems to be there seems to be like a relation of 100 between the two, right? If we decrease it again, we can see we're now at a base current of 5.199 nanoamps, and we have a collector current of 520 nanoamps, which very obviously has the factor 100 between them. So this is kind of this is like one of the main rules for the transistor. It's actually, I think it's not that complicated. It's actually just whatever current is flowing into the base, you will have flowing into the collector times 100. And you should also combine this with what we learned before. This is independent of the voltage at the collector, as long as the voltage is above the base voltage, which will get important in a minute. But again, like if I raise this to 1 kilovolt, I saw a jump here. So apparently there is a small jump. 522 nanoamps. Oh yeah, seems to be interesting. Let's go back down to 10 volts. Yeah, but it's marginal. Here we have 526. Here we have 525. So apparently there's like a very slight effect if you really ramp the voltage here up. But generally, I would say it's a good rule of thumb to say that the relation between base current, collector current is just the base current, the base current times 100. Okay, but now the next question, and it's the question that you asked in the chat, is why is this, like, why do we get such an extreme increase in voltage if we just, why do we get such an extreme increase in current going through the transistor for such a small increase in voltage at the base, right? So you can see it gets moving, and now if I get up to 500 millivolts, it gets moving even more. If I go up to 600 millivolts, it gets very extreme. And the answer to that lies in what I told you before, in the fact that you have this diode between base and emitter. Now, strangely, like I don't have like a good, I don't have a good analogy for this, but I mean, as we saw with the regular diode, we also have an exponential relationship between, whoops, that's not right. We also have an exponential relationship between the voltage up here and the current going through it, right? Oh, now it doesn't. It's because of the model, right? Okay, so with this model it actually works. We also have an exponential relationship between the voltage here and the current going through the diode, right? And so the transistor is also a semiconductor device. So it just, I think for now, like for me, you would just have to take it like that. A transistor kind of just likes to behave exponentially in a way. Maybe that needs to be enough for the moment. But basically, just what happens is that the current going into the base will turn the transistor on in a way, and this will allow for more current to go through the transistor. Like that's the best I can do at the moment. And it does so, like the base current, no, actually the base voltage influences it in an exponential way. And this is the second point that I saw in the chat. I think Martin said that a transistor is a current control device and not a voltage control device. And this is something that you will read a lot. And it's a way to look at it, but the problem is you can't separate the two. You can't look at just current or at just voltage, because the problem is that a current is always the result of a voltage, right? So let's say we have 0 volts here. So there is no voltage difference between the base and the emitter. So in effect, we have no current flowing, because in order for there to be a current, we need to have a voltage difference, right? So if you go really back to the basics, you could say that the voltage is the pushing force and the current is the movement. So there can be no movement without a pushing force, right? So if there's no force here and no force here, then you will have no movement. So nothing will happen. Conversely, if we do have a pushing force here, then we will start to see movement, like however slow. Okay, so you can actually see it. So we have movement coming from the voltage source and going to ground. But this is only because we have a voltage source here. That's what I mean with when I say you can't separate the two, right? And now back to the whole exponential thing. So the exponential stuff is actually in the relation between the voltage here and the current going through the transistor. So if you have a linear increase in voltage here, you will have an exponential increase in current going through the transistor. That's how it works. And that's also why our VCO worked, right? Because we have our CV, which is kind of increasing linearly. So like, you know, on the volt per octave scale, you have kind of, let's say you have C at 0 volts and you have C1 at 1 volt. So there's 1 volt between those two values, and then you have C2, which is at 2 volts. You have C3, which is at 3 volts, C4, which is at 4 volts, and so on. And there's always a linear increase in voltage between the octaves. So it's always 1 volt. But like I said earlier, in music, and frequency, you have to have an exponential increase. So the frequency always needs to double. And that's what we used in this kind of circuit, because we increase the voltage here linearly and we get an exponential increase in current flowing through the transistor, which means that the frequency of our oscillator also increased exponentially. That's what we used there. And again, this is something that we will just have to take at face value. But I think it's a good help already to know that I used to also think this way, that you always have to have a resistor between the voltage source and the base, and that it's only about the current that is going into the base. But it's not exactly true, like I said, because you can't separate the two things. Okay, that being said, what else do we need to talk about here? Maybe I will go into the chat and see if you have any questions that I can answer. Does anyone know if this will be available to watch afterwards? Yes, I put these in an archive basically on my Patreon, and I make them private here on my channel. So if you want to watch them, I would encourage you to get on Patreon and watch it through there. I mean, of course, there are other means to watch it, but I would just ask you, like, if you find my content valuable, then it would be nice if you could join the Patreon. I mean, of course, the other videos that I have, they are free, and they will always be free in the future. So all the proper episodes that I do are going to be freely available. It's just this kind of content that I would like to put behind a paywall. Okay, let's go on. Let's see. I appreciate the two circuits being separate. Thank you. Yeah, I thought it would reduce confusion. Good to know that it does. He should show the IV characteristic curve to explain this. I think I showed you this already. If I didn't, please, or if you think that I didn't, then please tell me again. You are the reason I'm going to study electrical engineering. It's very flattering. Good to know. Good luck, man. I hope it works out well. Yuri says, I always thought any silicon transistor won't open with VBE less than 0.6 volts. Yeah, those are like the kind of lies that you are being fed. It's kind of a simplification that kind of works. I mean, as you saw, we can look at this again in a minute. As long as the voltage at the base is below, something like 500, 550 millivolts, the current is actually negligible that will be flowing, but there will be a current flowing, right? So it's not that there's no current flowing. Like, the transistor will turn on gradually. A transistor is not a digital device. It's analog, and that's why it will turn on gradually. So this is something that you kind of have to you have to talk to your tutors. Like, if they tell you this, it's like a simplification that helps in some scenarios, but it's not true. It's a lie. Okay. Why is there a current from B to E if the voltage applied to B is lower than the forward voltage of the diode inside the transistor? Again, that's a lie. You have a current flowing. Also with diodes, it's the same thing. If you take a diode and you apply just 100 millivolts to the diode and you ground the other end, I forget if it's the cathode or the anode, but the other end you ground, and you just put 100 millivolts there, you will have a current flowing there. It's not blocking. That's a lie. Okay, next thing. In digital electronics, there should never be an ambiguous voltage that would obviously result in errors. Yes, in digital electronics, you would always try to make sure to have discrete states, but still, it's never clean cut in electronics. It's never that you have anything like black and white, one or zero. Like that just doesn't, that's just not there. Okay, Phobos, isn't 0.6 volts to fully open it? Yeah, we will look at that again in a second. I wouldn't say it's 0.6. I think it's like around like 0.7. It also depends on the device that you have. It's just a value like where the transistor like will be close to being a short circuit. So at that point, it's like so open that it's basically like a short circuit, and most likely you will fry your transistor if you push it so far. So yeah, we'll look at that again in a second. Eric says, the terms tri-state and high impedance don't come into play with transistors, just voltage leakage. Tri-state, to be honest, I saw this term a few times. I'm not entirely sure. I think I read something and it made sense, but I forgot about it already, so can't tell you. High impedance transistors, I think, are generally, like, people generally say they are like, have like a medium impedance input. I'm not quite sure, but we will get to that when we talk about amplifiers, which we will do in a second. Okay, so Kyler says the base emitter voltage varies with temperature, current, etc. I think you could also say that the current changes with temperature. Like, that's at least how I kind of picture it. You know, if you warm up a transistor, then it will let more current through, basically. And this will also have an effect on the voltage, because, of course, if more current is going through the transistor, then this will influence the voltage at its terminals. But yeah, in most cases it's around 0.6 to 0.7, but it will allow current to flow anywhere the base emitter junction is forward biased. True, that's true. It grows a lot past the junction potential, which is what the 0.6 volts is. Yes, exactly. For tri-state, you need 2 transistors. That might very well be. Justin says tri-state is on, off, or high Z out of circuit. So open circuit, you mean? Makes sense. Okay. Okay. So I will go back into the simulation. And so now, just for illustrative purposes, I will show you what happens once we increase the voltage at the base past a certain level. So at 600 millivolts, we are already at 1 microamp going through the transistor. If we bump it up even more, let's go to 650. We have 8 milliamps. If we go up to 700, we have 56 milliamps, which is already a shitload of current, 800 millivolts. Now we're at 2.7 amps. I think at this point, most transistors will go up in flames. I assume, at least, unless you have like a power transistor, something like that. 900 millivolts. Now we're at 129 amps, which should set off the fuses in your house. And once we go up to 1 volt, then we have 6.178 kiloamps. At which point the power plant might call you and ask you what the fuck you're doing. So yes, as you can see, I mean, we could push this further even. At some point, I guess the simulator would say no. 295 kiloamps, 14 megaamps. Yeah, I guess you see where this is going. So this is what I mean when I say you can't separate the base voltage. You can't say it's only about current, because, you know, the voltage does influence it. I mean, realistically, you won't be able to push it this far, because, you know, in order to have 1.2 volts here, you can see down in the corner, you would need to provide 140 kiloamps to be able to push the voltage at the base up to 1.2 volts. So probably not going to happen with the power supply you have at home. And also, you know, the transistor would fry before you even would get anywhere near that. So, but yeah, theoretically it would be possible. But okay, let's go down to a more reasonable level. 550 milliamps, right? Okay. And I think what I would like to do now is something that has mystified me for the longest time, which is just a very standard amplifier. I would like to build a very standard amplifier with this transistor here. And I mean, I guess you all know the configuration, how it's set up. You have read about the common emitter configuration and everything. And people always act like if it's like so self-explanatory, it's so easy, you know, just do this, do that, put a resistor here, and then you have an amplifier. Still, I would really like to talk about this and you know how it works, because I feel like it is very illuminating once you kind of get what's actually happening. So what I will do is I will set this up in the way that you usually see. Or actually, this is probably a simplified version of what you would normally see. So I will put a resistor here between the collector and the voltage source, and I just arbitrarily picked a 10K. I could have picked a 5K, I could have picked a 20K. For now, it doesn't really matter. Okay, and what I will do now is, like, this is what I mean with that I kind of simplify it. I will put in an output here, as you usually do. So you, with a common emitter amplifier, you pick up the signal from the collector. You have your output here, and I will get rid of this thing. I will put this output down there, and we will only look at voltage. We won't look at current, because you know, this is usually the configuration you would use for an audio amplifier, right? So we only look at voltage. And then what I will do is, like, normally what you would do here at the base is you would put in like a voltage divider to bias the base, and then you would AC couple the signal to the DID. And for now, we will get to that in a second, but for now we would just jump over that and instead use this lovely, oh no, not true, this is not lovely. We will use this lovely AC voltage source. So let me replace that. I'll put this in here, and of course it screams because right now this is a 10 volts peak-to-peak signal, and as we saw before, if we apply this to our transistor space, we get insane amounts of current flowing, and the simulator doesn't like that. So we need to pull this down. Okay, but what I will do for now is I will put 0 for the max voltage, so we will have no oscillation. And instead, what I will do is I will put in an offset voltage. So we had 550 millivolts before. That's what I will do again. And this might be a bit confusing at the moment, but what happens now is that this is not an oscillation. So instead, you can see in the bottom right corner it says V equals 550 millivolts. Right. So what happens now is that we apply 550 millivolts to the transistor's base, which results in, you can see that we have 1.7 microamps going into the base, and we have therefore 100 times that as a collector current. So we have 171 microamps flowing from collector to emitter. That's the situation. And now I need to dimension this properly, and I will get to this in a second. I will just try to set this up in the ideal way so that it works as an amplifier. Should be somewhere around here, I guess. Yep. Maybe here. That's not correct. Let's go here. Yes, it's perfect. And what I will do now is I will introduce an oscillation. Because right now we only have the offset. So right now I have dialed in 582 millivolts, and it's currently constant, so there's no oscillation going on there. And now what I can do is I can add in a very tiny oscillation. So let's go really tiny. Let's say we make the voltage oscillate by 1 millivolt. So it's going to be oscillating between 581 and 583 millivolts. Let's see what happens. As you can see, we have a signal at the output. And if I stop this, again, remember, the input signal is only swinging 2 millivolts peak to peak. And what we see here is our output is swinging between 5.85 volts and 6.3. That's, how much is that? 500 millivolts? I think that's 500 millivolts. Roundabout. A bit more. Okay, so, and this is like the completely simplified version, the stupidly simplified version of a transistor amplifier. It's called common emitter, and the terminology never made much sense to me, but all it means is that the emitter is grounded and that we pick up our signal from the collector. Okay, so I'm going to explain this more in depth in a second, but I just want you to marvel at the fact we have 2 millivolts peak to peak here at the input, and we get about 500 millivolts peak to peak swing at the output, which is crazy. Like, it's a crazy amount of gain. Okay, so now the question is going to be, how and why does this work? And I would say there is, like, we actually know all the pieces of the puzzle already. So in order to kind of make this clearer, what I will do is I will take this oscillation again away again, and I will go back to our voltage source. What I will do is I will take a variable voltage, and I will say I will dimension it the exact same way that our oscillation is kind of dimensioned. So I will say the minimum voltage is 581 millivolts, and the maximum voltage is 583 millivolts. Boom. Okay, so if I move the slider, then we can go from, we should be able to go from, come on, run this. Yeah, we're able to go from, why is this highlighted? What the fuck? No. Oh God. What is happening? This is super weird. Okay, works like this. Cool. So now, if I drag this slider, I can make the voltage here go from 581 millivolts to 583 millivolts. And if we go into the middle again, we go just right here. There's another ambulance, sorry. So what we can see now is that at 582 millivolts, we have a base current of 5.8 microamps going in here. And so we have a voltage of 6 volts at this point. If I increase the voltage at the base, we can see that the voltage here decreases massively, like in proportion. Like, it goes down to 5.8 volts. And if I decrease the voltage here, we can see that the voltage here goes up to 6.3 volts. And now the question is going to be, why? Like, what exactly is going on here? Why do we have this strange amplification effect? And to answer this, we have to look at two independent factors, basically. So drag this down a bit. I think this might be a bit helpful. So we separate this a bit more. Okay. So what I will do is I will build an analog circuit, like something that is what's the word? An analogous? No, I don't think that word exists to what we see here, but just with resistors. So I will also take a power supply here. I'll put this power supply in here. I will also make a 12-volt power supply. I will turn this into a 10K resistor, and I will turn this into another 10K resistor. And then we are going to put in another output, and we will put this in another oscilloscope. And then we will compare these two circuits. And you might already notice that, interestingly, they seem to behave the exact same way. So at this output, we have about 6 volts. At this output, we have about 6 volts. And the question is probably going to be why. And to understand this, we kind of have to understand how a voltage divider works. And I hope that most of you do understand this. But the gist of it is basically that if you set up two resistors like this, one is connected to a positive voltage, the other one is connected to ground, and you look at the voltage in the middle between them, then what will happen is that the voltage here in the middle is completely determined by the relation between these two resistors. So if they are exactly of the same value, then what happens is that whatever voltage you apply up here, you will get half of that voltage down here. So we have 6 volts, we applied 12 volts here, and we have 6 volts at this point. And this is just because they have the same value. So just to illustrate this, we're now at 10K. If I bump this up to 1 mega ohm, if I bump both of them up to 1 mega ohm, then we still have 6 volts. Because it is not about the individual resistor values, it is about the relation between the resistors, basically. So let me go back down to 10K. Boom. Okay, again, same resistor value, it halves the voltage. So 12 volts here, 6 volts at this point, right? Now we have to kind of understand why. So the way that I kind of like to visualize it, like I kind of moved away from the water analogy here because I didn't really feel it works that well. So let me try something else and you will have to tell me if this makes sense. So how I like to picture it basically is if you think of the resistance of both of these resistors as distance. So just roll with me here. So imagine that the distance between our output and the voltage source is 10K. So it's 10K units far away. And it's also 10K units far away from ground. Then this means that it's halfway between the supply voltage and ground. So it's exactly in the middle. So it's as close to ground as it is to 12 volts. And this means, I mean, just logically, this means if you're in the middle between the two, then it would mean that you get, and this is kind of where it falls apart, but this means that you get half of the voltage. I hope this makes sense. And now if we take this analogy and we say that we increase the distance between our output and ground, so let's say we bump this up to 20K. So now what happens is, the out is closer, so it's only 10K away from the voltage source, but it's 20K away from ground. And this means, since we're closer to the voltage source, we get more of that voltage at this point, right? Because we're closer to the voltage source. Conversely, if we drop this resistance here down, then this point kind of moves closer to ground, and it's like proportionally, it's now further away from the voltage source than it is from ground. So this means that the voltage here drops. We're now only at 4 volts. And if this is sufficient, like if this kind of makes sense to you, then we can use this model to look at what is happening in this circuit. Before I do that, I will go check back into the chat and see if you guys have any questions. The transistor maintains 0.6 volts between base and emitter because of the emitter internal resistance and resistance between emitter and ground. That is not true. It doesn't maintain 0.6 volts, just as a diode doesn't really maintain, like it's always said that, you know, a diode drop, it's 0.6 volts, blah, blah, blah. It's not true. If you push enough current, or if you have a strong enough voltage to push into the diode, you can raise the voltage. You can raise it past 0.6 volts. Like we saw earlier, if you have kiloamps, you can actually pump it up to 1 volt. It's definitely possible. Okay, Eric, just asking about isolation earlier. So there's an upper and lower voltage threshold where you have analog behavior. No, it's always analog behavior, like Parkler says. Exactly. Christian, what does biasing mean actually? I did not understand it so far. Yes, I will get to that in a second. Phobos was AFK, not sure if he mentioned it, but biasing is basically just setting a default state voltage. For a symmetrical waveform, it sets the center voltage. Yeah, we'll get to that in a second. AC is half the time negative and half positive. Yeah, we'll get to that. Justin also explains the biasing stuff. Kyla says, common emitter means the input and output are reference to the emitter voltage. Input is connected between emitter and base. Output is taken from the collector and emitter. Yes, that is how it's defined. Okay, so if there are no more questions, then I will get back to it. I hope the analogy that I just mentioned makes sense. So maybe here's another thing that I also like to think about. And this is factually very wrong, but it helps me to think about this. So again, if we think about this whole situation, And if we go back up to 10K, then we could say that you know, this resistor kind of restricts the amount of current that's flowing through here, right? That's flowing from the voltage source through here, through the other resistor into ground. And it's only letting a set amount pass through. And then we have the 10K, which is the same value as this. So it will kind of, you know, it's wrong, but it will let like the same amount pass through it. And that's why we have half of the voltage kind of lingering around here, or rather half of the current is like hanging around this point, which causes the voltage here to be raised. And if I increase the resistance here, then in my mind, like how I like to picture it, is that the current that is going through this resistor kind of gets to, and again, this is really wrong, but it kind of gets to hang out at this point because the resistance here is so much stronger. More current will hang out here and it will kind of increase the voltage, right? Because it's blocked from escaping to ground, basically. And conversely, if we drop this down like really far, then all the current that is passing through this resistor can basically just almost immediately leave because the resistance value here is so small. So the current doesn't hang around here much, and so the voltage here drops very far. So now we're only at 1 volt, right? And if we drop this even further, whoops, then most of the current can leave and not a lot can hang around here. And so now we're only at 118 millivolts, right? And again, if I bump this up to 100K, then again, the path here is really blocked. So only a very small amount of current can flow. And that's why more current can hang around this point and it raises the voltage, right? So the resistor value here, basically, like if we increase it, we get more voltage because we get kind of a, what's the English word? In German, it's Stau. Let me look this up. Congestion, a jam. Yeah, that's how I like to picture it. It's like a traffic jam, you know? So there's a traffic jam here. So there's a small, there's a mild traffic jam here and a big traffic jam here. And that's why like a lot of angry people are kind of accumulating at this point and they are raising the voltage. But if there's only like a very, very minor traffic jam here, then all the people that are coming like through this traffic jam can easily like go home through here because, you know, their path is only slightly impeded. So there's a lot less anger at that point, at this point here. And so there's no voltage here. Maybe that works. I don't know. Let me know. Okay. But with this kind of model in mind, let's go back to our amplifier here. Applying the same model, what we can say is we have the same 10K resistor here, right? So we have a minor traffic jam here. So only a limited amount of current can go through this resistor at any time. It's not a wide open road, it's a traffic jam. And then we have another traffic jam down here in form of the transistor. And like we saw earlier, the amount of current that is allowed to flow through the transistor is directly controlled by the voltage at the base, right? Or rather, by the difference in voltage between the base and the emitter. And so what happens basically is, again, if this analogy makes sense, you know, we have this traffic jam, we have people going through this traffic jam, and they kind of hang around at this point because this is not very open. It's kind of open, so a decent amount of cars can kind of go through, but still a lot of people have to hang around here and they raise the voltage because they're very angry. And now, if we open the transistor up more, right? So if we increase the voltage here, maybe we can make this a bit more clear. If I go up to 590 maybe, let's go from 580 to 590 millivolts, right? Okay, so let's go back to 580. So at 580, we have 6.5 volts at this point. So a lot of anger here. And if we increase the voltage at the base here, then what happens is that the transistor opens up more, it lets more current through, it lets more cars through. So it's a smaller traffic jam. It's kind of equivalent as to when we were like lowering the resistance here at this point. And so what happens is that the voltage here drops. We can simulate this by saying, okay, so we have 3.9 volts now here. So if we want to match it, we would probably have to drop this down to something like maybe 4K7. Yeah. So what happens is basically that we allow for more current to flow through the transistor, which means that more of the current here hanging around here can leave, which means that the voltage here drops, right? And this is kind of what we're exploiting. So as you saw, a very tiny change in the voltage at the base has a huge effect on how much the transistor opens up. And that has a huge effect on the voltage at this point. Because again, if the transistor is very closed, then more current will accumulate here, giving us a raised voltage at this point. If we open up the transistor, and again, the relationship between base voltage and transistor current is exponential. If we just increase it slowly, slightly, the voltage here, then the transistor will open up a lot, and the voltage here will drop a lot, right? So here at 580 millivolts, we are at 6.5 volts, and at 590 millivolts, we are at 3.9 volts, which is an extreme difference. It's almost half. Right? So a tiny change in voltage here sees a big change in voltage at this point. And this is the whole secret. This is how this transistor amplifier works. Because now if we exchange this thing for our oscillation, then as we saw before, we have a tiny oscillation here. We have 1 millivolts peak to peak. So it's swinging between 581 and 583 millivolts. So what happens is we slightly change the voltage here, and the voltage at this point changes a lot, right? So if we increase this a bit more, so let's say we go up to 2 millivolts. Oh, that didn't take. Let me try it again. 2 millivolts. Then we can see like how massive the change here is, right? So, and this is because already if the signal is swinging like 2 millivolts peak to peak, then the openness of the transistor will kind of vary like extremely. Like it will open up a lot, and then it will close down a lot, it will open up a lot, and so it will like relieve the traffic jam here, and then it will not increase it. It will make it worse, it will make it better, it will make it worse. So more cars are stuck, less cars are stuck, more cars are stuck. So voltage rises, voltage drops. That's the effect of this. Okay, so I will check back in the chat and see if you guys have any questions again. One thing, if we want to show current voltage rather than across time, showing the voltage on the out would be more helpful rather than on the scope. Right click, check voltage on I know what you mean. I know what you mean. That is probably a good idea. Is it in edit? Yeah. Right. I mean, now I'm back to the oscillation, but still, that's a good tip. Eric, a sine wave at control voltage would be amplified and 100 degree at out. Yes, that is the effect of this kind of amplification. Because, as I said, if we increase the base voltage, the transistor opens up more, which will allow more current to go to ground from this point, which will cause the voltage here to drop, right? So voltage increases here, voltage drops here, voltage drops here, voltage increases here. So yes, we get a 180 degree phase shift basically. Okay, and now just to make it more explicit, because Christian has asked about it, the question of biasing. So this is a word that you see like thrown around a lot in relation to transistors. So it's always a question like, how do I bias my transistor? Why do I have to bias my transistor? What is it? And the thing is, we have already done this. We have already done this here. And I will explain to you why this is necessary. Now I'm thinking like, should I stay in here or should I work with a voltage divider? I think for now I will stay in here. So I think someone already said in the chat that what you want to do is by setting an offset, you want to kind of set like I think it's called the quiescent point. It's like the what's the proper way to put this? It's kind of the neutral state that the transistor or that the amplifier sits in when you have no signal at the input. So we can get there again if we put a 0 here, which means that we have no oscillation going on. You can see this down here. There is no oscillation in our voltage that we are applying to the base. So this is a steady voltage, right? And the steady voltage is, I can show it again to you if I oh, maybe we can do that again and use another output here. And we can say show voltage. And then, yes, then we can see better maybe. Like this is the base voltage and this is the collector voltage. Okay, and because I have put in a DC offset of 582 millivolts here, you can see that the base voltage just sits at those 582 millivolts and it doesn't change, right? Because for oscillation, we put 0. And you can also see, like when I chose this value earlier, you can see that we get about 6 volts at the collector, which is exactly half between 12 volts and ground, right? 6 volts. And we can go back to this again here also. Boom. And I can also do the same thing, which is a good trick. Thank you. And now the question would be like, why should we do this? Why should we put 582 millivolts exactly in here so that we get these 6 volts here? And the answer to that, I think someone already said this in the chat, is that we need to have enough headroom upwards and downwards for our oscillation to kind of be amplified, undistorted. So let me show you what I mean by this. So let me dial in a different offset. So let's say we go very extreme. We go down to 400 millivolts. And what this means is we reduce the voltage at the base, which means that the transistor closes down, which means that the traffic jam here gets really bad, which means a lot of cars, a lot of current hanging around here, a lot of voltage. So we are at 11.995 volts, which is very close to 12 volts. Actually, just as an experiment, if we drop this down all the way to 0 volts, you can see that since the transistor is now fully closed, basically we get a complete jam here, and so we have the same 12 volts at this point as we have up here, because none of the current can leave through the transistor. So it's all just staying here, and we sit at 12 volts. Okay, but let's go back to our 400 millivolts. So at maybe that's also a bit too extreme. So let's, I keep clicking on that thing. Let's bump it up to 450 maybe. Let's bump it up even more to maybe 500. It's still not enough. Yeah, that's like the problem with these exponential relationships, right? It's still not enough. Let's go up to 550. Yeah, that looks better, probably. Okay, so now we have we use a biasing voltage of 550 millivolts. So this sits at a steady 550 millivolts, and this means that our transistor is opening up like a little bit and it's letting a bit of current through, and this means that the voltage at this point drops slightly. So now we're at 10.28 volts. Okay, now watch what happens if I introduce an oscillation again. So let's start small with maybe with 1 for now, with 1 millivolt, and let's see what happens. Okay, so we can see our output is, for now, it is still fine, right? It's swinging between 10.2 and 10.3 volts. So let's crank it up a bit. And it's still fine. Let's crank it up a bit more. And it's still fine. Okay, let's go up to 10 millivolts. And it's still okay. 20. Okay, now I'm realizing that we're only going down when we're not going up, actually. Why is that? Let's go really extreme. Okay, you can already see the distortion. I know we are going up. We're not going up enough to crash into the supply rail. So probably it would probably be a better example if we didn't bias it enough. So maybe let's go down to some, if we biased it too much. So maybe let's go up to 600 millivolts. And then we can bump this oscillation down to maybe 5 millivolts. Yes. And now I will turn down the speed somewhat. And now you should be able to see the problem. So let me drag this down to 0 volts again. And I will resume this. Okay. And now what we see is that in this neutral state, so we have 600 millivolts applied to the base. So the transistor is extremely open. It's really, really wide open. And this means that there is barely any voltage left at this point. So we are down to 166 millivolts. So this is basically nothing. And you will see that it's below the base voltage. You know, the transistor is so open that the voltage here drops below the base voltage. This is a very bad situation. You don't want to have this. And now what happens if we introduce our oscillation here, bump up the speed a little bit, is you can see that whenever the base voltage goes down, so when we go to, it's 598 millivolts, then what happens is that the voltage here goes up. The question is why? And the answer is, well, because the transistor closes down, and it closes down by a lot, and this means that the voltage here rises, which is good. So that's why we get like our spike from our triangle that we're putting in, right? So just as a reminder, this is how, oops, where do we see current? Yeah, okay, I can't show it like this, sorry. Okay, but just imagine like we should be seeing a triangle. Instead, what we see is like this weird, funny, distorted shape. And as you can see, the problem is that once the voltage goes close to those 600 millivolts, we basically run into the lower kind of, how could you call this? It's kind of the lower threshold of what the transistor is able to do. Because, you know, at some point, the transistor is so open that the voltage here can't drop any further, because, I mean, it's so close to 0 volts that, you know, the transistor can't make it go negative anyways. Like, this is the main issue. But also at some point, you know, it's just starved of current. So there's no cars that can go through here. So the voltage here can't drop any further, right? And so we get this plateau effect at the bottom. We get this, you know, this weird valley, this kind of weird untriangle looking valley. Now the question is, what can we do against this? What can we do about this, rather? Well, as we saw before, we can simply turn down the biasing current. Right? So let me turn up the speed. And now we can see that this is actually working again, because now, let me choose a bit of a less extreme difference. Maybe even more. Boom. No, this is still not enough. 595 milliamps. Yeah. So now you can see that we are always above the base voltage, right? So we are oscillating between, let me stop this, 1.4 volts and 2.9 volts. And 1.4 is way above the base voltage. And so everything will still work as expected. So we still get our amplification, and everything is fine. And so here we have actually enough headroom to reproduce the triangle in the upper and in the lower corner, basically. And but still, if we wanted to increase the gain now, we could actually run into trouble really quickly again, because as you can see, I mean, we're at 1.1 1.4 volts, and this is fairly close to those about 600 millivolts at the base. And remember, like, we can't go below that. As soon as we go below that, we get distortion in our signal, right? We cut off the bottom basically. And so this is not ideal. And now the next question might be, well, yeah, but how do we actually increase the gain, right? Because we said earlier that our transistor, remember, like, our transistor has like a kind of fixed gain of 100. Now the question is, like, how do we even increase the gain? And the answer is actually very simple. We need to increase the value of this resistor. I can demonstrate this to you. So let me go up to 12K maybe. And as you can see, we are already running into trouble. So we are already running into the lower rail basically. Okay, so let me push this up a bit again. Okay, so what I've done now is I have decreased the biasing voltage to 575 millivolts. So if we go down to 0 again here, you can see that we sit at 6.5 volts, which is kind of nicely centered between these 12 volts and ground. So the quiescent point, the kind of point like where nothing is happening, the neutral point, is now at 6.5 volts. So we have plenty of room to go up from there. Like, we can go up to nearly 12 volts and we can go down to nearly 0 volts. So there's a lot of space towards the top, a lot of space towards the bottom, which is a great thing. And that is why now we don't run into the bottom rail. The question is, why does it increase the gain if I increase the value of this resistor? And the question is, does it even really do that? Maybe I'm just talking bullshit. I think it does. But we need to adjust. Let me just try to see if I can actually get like a decently loud signal from this. Okay, maybe I'm actually talking smack. Let me go up to 100 and let me drop this down. Okay, so I'm actually talking smack. Okay, so this is bullshit. That is not ideal. I thought that this was how it would be working, but apparently it's not. Let me check the comments if anyone said anything about this. So, Chris, the concept of current hanging around is bad. Changing the current flowing through a transistor also affects the current flowing through a resistor. Yeah, I mean, that's why I said it's bad. It's a kind of bad way to think about it. But I think if you're very new, it can, in a way, help. Maybe it doesn't. Phobos, might be useful to show the input signal above it since it is inverting. I can try to do this. Shouldn't the triangle signal be exponentially distorted somehow? It looks linear. Yeah, that's also something we can talk about. Okay, but first let's figure out this whole gain mess. I mean, maybe it really doesn't matter what kind of resistance I use here. I think that might actually be the case. So maybe I was really talking smack. If so, I would be very sorry. What does it have to do with the? Of course it does have. It has to do with the biasing, with the bias voltage, right? So if we increase the bias voltage, do we then get a bigger voltage swing? It looks like that, right? So let's increase this even more. Let's go with 600 M. Okay, let's drop this down. No, that's not more gain. That is not more gain. That looks like it's more gain. It's very hard to say. 3 point. No, it's not more gain. It might be more gain. Someone help me here. Let's drop this down to 590. 600 millivolts. Oof, now we're swinging from 752 2.2. I think it is more gain. Okay, maybe someone in the chat has an idea how we can, or if it's actually influencing the gain. But for now, let's talk about the topic of linearity, which is an interesting one. So someone asked, why is the output signal here, why does it look like a proper triangle? And the answer is because our input oscillation is so small. So, I mean, the thing about exponential curves is if you take like a very, very tiny bit of an exponential curve, like you isolate just a tiny stretch of it, it actually looks like a straight line. It's not a straight line, but it looks like a straight line, right? And so that's what's kind of happening here. Since the oscillation we are applying to the base is very tiny, this means that our output signal kind of looks like it is, like as if it's undistorted and linear. But if I increase our input signal, and of course I also need to adjust the biasing. So let me push this up a little bit. And now you should already be seeing that our triangle got a little bit fat, right? So it did gain a bit of weight. So, and let's push this even harder. And now you can see that it's like even rounder, you know? So it's looking even more like distorted and weird. And we can push this really to the extreme. Let's go up to 35. Yes, and we need to adjust the biasing. And now I guess now you can, it's really obvious that this is distorted. And that is the effect of what I just described. So since the input signal is now much bigger than the 2 millivolts that I had before, we are now, it's as if we are taking a bigger chunk of the exponential curve, and now the curve begins to look like a curve, like it's no longer a straight line. Like now we are actually seeing this exponential kind of distortion. So that's why in kind of all of these transistor amplifier circuits, and I think every time like semiconductors are involved and you're amplifying something, you will have this restriction that you need to cut your input signal way down. Like you really need to cut it way down. So in this case, I think at 5 millivolts, it might look undistorted. I think it's still it's already a bit rounded, but this might be something that you could live with. It's always a decision that you have to make when you design these circuits. So you have to look at, you know, how much input signal can I put in? Like how much distortion am I willing to live with? You know, these are decisions you have to make in the end, and probably you have to just consult your ears and listen to it and decide if it sounds nice. Maybe you even like the distortion, so you purposefully go for the distortion. But yeah, that's basically just how that works. Okay, let me check back in the chat. You have the right idea. The gain is approximately the ratio of the collector and the emitter resistor. Yeah, that's what I thought, but I feel like the biasing current kind of plays into it as well. You know, I thought it was easier to demonstrate, but yeah, kind of got hung up there. Bypass capacitors can help reduce the emitter resistor degradation. Yeah, I think also like putting in a emitter resistor can, you know, fix some of the beta dependence. Did it, but I think it goes too far right now. If you right click the resistor and hit slider, you can make a slider. Yeah. You mean the one at the top? Yeah, we can try that in a second. Okay, James says AC gain is given by minus RCRE according to my university textbook. Do you not need a resistor at the emitter? You can put a resistor between emitter and ground. I think this is called emitter degradation. Kyla, correct me if I'm wrong. And this is mostly done to control the transistor's gain. So as I said earlier, the problem with transistor gain is that this beta is highly variable between transistors, and I'm not sure. I think also with transistor operation, I think that there's also some weirdness going on there. And so putting a resistor between emitter and ground can, I think, can kind of reduce the effect that the beta has. So it makes the gain more uniform between different transistors, I think. I think that is how it works. Okay, QP says, think about how much current flows through the resistor. The voltage drop is calculated by Ohm's law. Yeah, that's what I thought. Like if I increase the resistor, then we should see a larger voltage swing, because there's less current going through it. That's what I thought, but apparently it doesn't work as easily as that. Eric says, this is NPN. Would PNP not invert, or does the output move down between the emitter and ground? Still inverted. PNP is basically an NPN, but just with with everything reversed. It's like the Bizarro twin. It does everything opposite in the opposite way. We can try to substitute the NPN here with a PNP in a second. Kyla says, common emitter always inverts. Yes, because if you would set up a PNP in the common emitter configuration, you would also need to flip everything on its head, and so you get the same result, I think. George says, RE limits the current just as a regular resistor between V plus and ground would. Yes. GD, if I remember correctly, the emitter resistor increases linearity, reducing distortion. I think it also makes VBE change less, but I'm not sure. Yes, I think it also makes it more linear. Yeah, it's basically, I think I saw it. I saw people call it negative feedback, kind of, and we can look at that in a second. Eric asks, does phase shift affect audio? No, it doesn't. I mean, generally, like if you just have this one signal, so let's say you have an oscillator and you have like 180 degrees phase shift and you listen to it, it will sound exactly the same. This will only become an issue if you mix the non-inverted and the inverted signal, because then they cancel out, right? Or if they're not exactly 180 degrees phase shifted, they will, you get these weird phasing effects. So in that scenario, it's important, it can matter if it's inverted or not. If it's just the signal or it's only listening to, it doesn't matter at all. It will sound exactly the same. Kyla says, the emitter resistor is for thermal stability. Yeah, I think all of those things, no? If I'm not wrong. GD says you can't hear phase shift, but it's something you need to consider when designing circuits. Yes. Also, it's important when you are talking about control voltages. If you have an envelope, for example, you invert it. Yeah, it does a different thing. Wilson says, in the scope of the output, click the cog to open the properties and display peak-to-peak voltage to see the size of the output wave. We'll try this. Where is the cog? The cog here. Okay. And what did you want me to click? Whoops. No. Whoops. Where's the window? Here's the window. In the scope of the output, click the cog, display the peak-to-peak voltage. I have never done that before. Let's check whether it is vertical scale, no. Horizontal scale, no. Plots. Show spectrum, log spectrum, no, that doesn't seem to be what you mean. Show info. Show frequency, show average, show RMS average. Show peak value, show negative peak value. Maybe that's what you mean. Let me know if you mean something different. Okay, let's get back to it. Eric asks, I wonder if this software would bog down my Raspberry Pi. You mean the circuit simulator? I guess so, yes. I mean, it already kills my MacBook, so yeah. Patrick, as an example, a delay line would alter the phases and not really affect the signal unless it's mixed with a dry signal, like in a flanger. Yeah, that's what I meant. James says, to control the gain, the AC swing in the output, it's controlled with the value or the value of resistor at collector divided by the resistor on emitter. Example, gain -5 would need resistors RC by RE -5. Yes, but like I said, you can also, I think you can also increase the gain without having an emitter resistor. phobos. Phase shifting actually happens all the time depending on distance. So one way how EX can determine location. That makes sense. Okay, so that's it with the comments. So let us try to increase the gain without having an emitter resistor, because I am fairly confident that it should probably be doable. Okay, and if it doesn't work, we will just give in and try with the emitter resistor. So let's bump this up so that we are properly centered here again. And so now we can see that we have 5.6 volts here, and we have 7.7 volts here. So that would be 2 volts peak to peak now. And now the mission would be to increase this. And what I would try to do, would just intuitively, like if I, it's what I just said, if I wanted to, oops, I think this is very annoying, so maybe I'll just take this out. If I wanted to get a bigger voltage swing here, so my intuition would be, if the resistor here is bigger, less current can flow through this resistor, and so when the transistor opens up, the voltage here would drop further, right? And I agree, like maybe I shouldn't use the concept of the hanging around of current, but it's still how I think of it. Maybe that's why this doesn't work. Maybe that's why. But yeah, what I would assume is that if I increase the value of this resistor, then kind of we starve this point of current more. Maybe we can say it this way, I'm not sure. And so the voltage swing should increase. So let's try this. I will push this up to 10 volts, add to 10K. And let's see if we have any increase in gain. Okay, speed this up. Okay, so now maximum is 7.2 and the minimum is 4.8. Maybe I should have written down like what the value was, right? So let's go back to this. Okay, so we have 8. That's about 8, and we have 6.1. Okay, so let me just quickly write this down. That would be 8 minus 6.1 is 1.9, right? 1.9 volts. Cool. So now let me increase the resistance here, and I will speed this up. So boom, boom, we get this quicker. Okay, so now we have. Oh God, no, I'm going to have to use the calculator. So it's 7.2. No. 7.12 minus 4.81. Okay, so now we're at 2.31 volts peak to peak. So as I expected, we did increase the gain. So let's see if we can increase it even more if we go up to 12K. Let's speed this up. And let's put this in the calculator again. So we are at 6.1 volts. And the bottom is 3.38, I think. Yeah. And that is 2.72 volts, which is again an increase in voltage. So actually I was right. I got insecure for no reason. So yeah, it's kind of like I expected. I think I expected the gain to ramp up more. But still, you can see an increase in gain. And again, I think it is like I explained. So less current going through here means that if the transistor opens up more, the voltage here simply drops further. I hope that's clear for everyone. I need to find a better way to visualize this, or a better metaphor. But yeah, it's just the voltage here gets weaker because you allow more current to kind of go through here and go to ground. You kind of suck this point dry, maybe. I don't know what a good analogy would be. But yeah, and I think at some point we kind of reach a point of diminishing returns. So let's go really crazy. Let's bump this up to 20K, and then we get the problem again that we're running into the lower, I don't know what to call this, the lower end of the output signal. So we need to adjust the biasing. So if we put this here, and that's where I think this comes in, that I think the biasing also plays a role maybe in the gain, right? So it's 7.8 minus 5.8. It's 2, right? So I think I'm correct about this. So I think this makes sense. Like if we decrease the biasing, we kind of go further down on the exponential curve, and so further down on the exponential curve, an increase and decrease doesn't hit as hard as if you're further up on the exponential curve, right? So as we saw earlier, like for example, when the capacitor was discharging, you can see that at the start, you have a big difference between points on the curve, and at the bottom you have like a decreased distance between the points. And so bit struggling with putting this into words. I hope you get this. So, if the starting point is lower, then an increase will hit less hard than if you're higher on the curve already. That's how I visualize it right now. Maybe that helps. But yeah, so we can see that once we have to adjust the biasing, then we run into the trouble that we also decrease the gain simultaneously. So that's why I think this is kind of a balancing act. So we need, if we really want to maximize the gain, and maybe we can try this right now. So if we want to find the sweet spot where we get like a lot of volume, I mean this might actually be it. Okay, so I think we can actually increase it a bit more. So let's go up to 575. Yeah, now we're really dropping down. We can go like 1 millivolt more. Boom, we can go even further. So let's go here. Ha, yeah. Now we're so close to the bottom. But you can see that we get plenty of gain. We have 3.95 volts at maximum. We have 182 millivolts at minimum. That is about 3.7 volts peak to peak, which is way more than we had before. Like before we had maximum was 2.75. It's not a massive improvement, but yeah, it's I would say it's a good amplification factor, especially considering that we put in 5 millivolts peak to peak and we get out almost 4 volts peak to peak, which I think is a good amount of amplification. Okay, so my question now would be, do we need to talk about biasing more, or is this kind of sufficient for you? Let me check the questions again. Will the stream be condensed into a short edited video later on? There's been a lot of useful information, but it's really long and a bit windy. Yeah, sure. Yes, I mean, like I said earlier, I'm working on the next like proper video, which will be on a transistor-based VCA. And in this video, I will kind of use all this stuff. So I will explain the basics of transistors again, and I will explain like how the voltage control stuff works. So in there, you will get most of the information, not all, but a good chunk, a good useful chunk, and that should hopefully help, I guess. So yes. How can you make symmetrical power supply for op-amps with DC input and high power output? I have a video on my channel on a power supply. Maybe you want to check that out. James said, I read the book a bit more. I see what you mean about the emitter resistor. Sorry for confusing things. No, you didn't confuse things. It's completely fine. And I mean, it's valid because the resistor at the emitter kind of adds to the, you can't really call it resistance, but the transistor, like how much current it passes through. So, it is related, definitely. Okay. Samir, hello, what are the limits of this configuration? You mean amplification limits? I think we maybe just reached it. Like in terms of amplification, I think maybe like, right now we are amplifying 5 millivolts peak to peak to almost 4 volts peak to peak. So this might be close to what the limit is. Maybe you could push it even further. We could try, but I'm not sure like what the benefit of this is. But yeah, you saw how it would work, I think. Okay. Eric, could you imagine if Joseph Fourier got a hold of a synth? No, I can't. Phobos says, I'd like to see you bias with resistors since that will affect the base current as well. Yeah, we will. Okay, then we will do this in a second. Lucas says, actually, I'm learning a ton watching this. That's very good. Like it's always weird, like doing these streams. It's just such a weird kind of talking situation because I'm sitting here alone in my room, and most of the time when I'm on the simulation, I don't see what you guys are saying, and obviously I don't hear your reactions or anything. So I'm all the time I'm completely unsure if what I'm saying actually makes sense or if it's happening anyway. So it's appreciated that you say it helps. So nice. Philip says biasing is about setting a so-called quiescent current point. Yeah, that was what we were talking about. We will do this in a second with resistors as Phobos kind of suggested. So QP says, yes, biasing techniques and decoupling from bias would be good. Yeah, that's what we'll do in a second. Asa says, yeah, but in configuration from your video, you use AC at the input of LM7X12. I used the TL074. Maybe that's what you mean. But I'm not exactly sure what you're asking, so you might have to rephrase that, sorry. Christian says, is this also a way how a triangle to sine wave would work? Sometimes the shape looks like a part of a sine wave when I play with the bias. I am unsure. I don't think you can achieve a proper sine wave with a single transistor. There is... yeah, you can use it to soft clip, but I think it would be smarter to maybe use diodes to do that. You can actually, I don't know if you've seen this, I can just show you. In the simulator in Felstat, what you can do is you can click on circuits and you can click on diodes, and you have a triangle to sine converter here. I will not click it now because otherwise my circuit here will be lost. But if you click on this, it will show you a way to use diodes to convert this. So, and it's based on a similar principle. So it's also like the same kind of exponential, like semiconductor-ish distortion that is used to turn the triangle wave into a sine wave. So yeah, that would work. Philip says, a little bit advanced topic is also so-called Miller effect, but this is topic for next episodes. I've never heard of that. I'm very intimidated by that. Also funny that your name is Miller. But yeah, I will try to look up on this. Okay, so my suggestion would be, because someone said that it was already long and windy, my suggestion would be, as a final thing, we will now try to make this into a real-world circuit. So we will try to bias it properly with resistors, and we will try to AC couple the input, and we will try to make it into something that you could actually build on the breadboard. And I think, like, if you guys don't insist on going further, I would probably then do a quick Q&A after that, and maybe you have some problems, and then probably I would end it at some point because we're already going for how long? 3 hours? Yeah, like close to 3 hours. So my voice is slowly going. Okay, so let's jump back into the matrix and let's see what we can do here. So first the question maybe asked, like, why no, it's actually not a good question. No, the question is, like, how can we take this magical source that we have here, where we can just freely change the offset and then change the amplitude of our signal, like, how can we translate this into a kind of real world thing? Because we don't, like, our oscillator from our VCO doesn't work like this. Like, you can't dial in an offset like as precisely as this and then, you know, just choose the amplitude as you could here. So that's not realistic. So it doesn't work like this. So how do we actually make a transistor amplifier? This is where biasing with a voltage divider comes in. So what we would do is we would first remove the signal, we would remove the offset here, And let's say we have a proper signal that's coming from our oscillator. So let's say we have a 10 volts peak-to-peak signal, right? So the usual thing. So we can see here that we are swinging from -5 to +5 volts, right? And now we would like to use this. We would like to amplify this. I mean, even though this is kind of like a stupid thing, because I mean, this signal is loud enough. So why would we need to amplify it? So thinking of it, maybe we should actually drop it down. So, okay, so this is maybe a bad idea. So let's maybe assume we've built a circuit, and let's say it's a filter, and the filter required us to scale the input signal like way down for the filter to work properly, like my diode filter, for example. For that, you have to like drop the signal down to, I think it's just 50 millivolts. So let's take this as a scenario. So let's say we have a voltage swing here of 100 millivolts peak to peak, and we would like to amplify this to, I'm not sure if I can deliver on this, but let's say we want to amplify this to 10 volts peak to peak, so to 5 volts positive, -5 volts negative. How would we go about this? Well, the first thing that we would need to do is, like before, we would need to set the base voltage here to a level where we get about 6 volts at this point, so that we have the headroom, so that we have 6 volts to the positive rail to 12 volts, and we have 6 volts distance to ground, so that we like square in the center. That's the idea. Okay, and in order to do this, we can use a voltage divider. So I put a resistor here, I put a resistor there, I connect this one to ground, and I connect the other one to a voltage source like this. Okay, and of course I haven't changed the values of these resistors, so it's just 1K. So what we get, this needs to be 12, of course. Whoops, this needs to be 12 volts, of course. Now what we get is 674 millivolts, and we get just 80 millivolts here, which is unacceptably low. So what we need to do is we need to reduce the voltage at this point. So how do we do this? Well, we can just increase the value of this resistor, right? Because that's how a voltage divider works. Like we looked at this earlier. If we increase the resistance here in relation to the resistance here, so if the resistance here in relation to the resistance here is higher, then the voltage at this point will be lower. Because, I mean, maybe the distance metaphor is better here. Now this point is way closer to ground than it is to 12 volts, and this means that the voltage here drops, right? Okay, and we can see that we still haven't succeeded at all, because we are at 29 millivolts, right? And this is way too low. We wanted to gun for about 6 volts, and so this doesn't work. So what do? Well, we increase the value of this resistor. Boom. And now I went way overboard. So I put a 47K resistor here, and we can see that this jumped up to 12 volts, which is bad, which is way too much. Like I said, I wanted to go to 6 volts. So let's drop this down to maybe 33K. Now we're at 11.998. That also doesn't work. So let's drop it down to 22K. Now we're at 10 volts, getting closer. 20K, 5 volts. Okay, so the sweet spot seems to be at probably 20K5. Also not. Okay, 20K4. No. 20K2? Yeah, that looks better. Okay, now obviously I don't have, like, I think nobody has a 20.2K resistor. So obviously we will also need to fiddle with this resistor here so that we get like a better kind of ratio. So let's try pushing this up a little bit, and then we can, whoops, no. Let's say 10K, and then we can bump this up a bit. No, this also doesn't work. Probably we would need to go proportionally up. That doesn't work. 200K. No. 195. I think it's closer, but it's still like a very weird value. So I would like to have more of an even value up here. So let's try to go like this maybe. No, this also doesn't work. 82K. Not enough. This is tricky. Okay, maybe now if we bump it up to 100K. No. Oof, this is super annoying. I'm very sorry. Okay, so for now, let's just go with the 200K here maybe. No, that also doesn't work. Now how would we have to drop this down to get this to a proper? No, we have to raise it up. 12K, no. 11K. No, this is really frustrating. Let's try it with 100K over here. Let's drop this guy down. Maybe here. I think I have 5K 2s. That's in the ballpark, I guess. 5K 1. 5K. Yeah, I mean, good enough, no? Let me check if someone pointed out that this is stupid. Use a potentiometer. That is a good idea. Probably that's what I would do now in a real life scenario. But for now, let's just put this to 5K1 and then we're close enough. Then it's fine. Okay, so what have we done here? Well, we used the voltage divider to set the voltage at the base. We set it to 566 millivolts. So now what's happening is that the transistor is open to such a degree that in conjunction with this 20K here and these 12K, these 12 volts here, we get about 5.5 volts at our collector as the quiescent point, as like the neutral point, basically. Okay, and now if we are very naive, we could try the following thing, which, spoiler, won't work. So we could try to simply apply the oscillation to the base together with our bias voltage. And as we can see, this basically just pushes our collector to 12 volts simply because our signal is basically eating up the bias voltage. So if I increase the current speed here, you can actually see this. So you can see that all the current that is coming from our voltage source here is going into the signal simply because the voltage is sitting at, it's swinging between 50 and minus 50 millivolts. So it is basically below the base voltage, so everything flows into our signal. And so nothing goes into the base. And so we basically, it's like I said, we haven't biased our transistor at all, so it just sits at 12 volts, which is a really bad idea. So what can we do about this? The solution is very simple. We need to make sure that this can't happen. Like, we need to make sure that the current coming from here is not allowed to flow into the signal. How do we do that? Well, this is a constant current, right? So this is a constant amount of current going from positive to ground. So if we want to block this constant current, we can use a capacitor. So if we put a capacitor here, and we dimension it correctly, probably this is overkill, probably too much, but let's put a 1 microfarad capacitor here, and then we apply our oscillation again, then we can see that all of a sudden the constant current is going, of course, like down here. That's the nature of the voltage divider, but it's also going into the base as expected. But at the same time, it is kind of being modulated by this oscillation, right? So every time this oscillation goes high, this current going into the base gets a bit stronger, and every time it goes low, it kind of sucks a bit of the base current away. So if I turn up the speed here again, you can kind of see this, how it's like speeding up and slowing down, right? So it's as if the oscillation here is riding on top of our base current that is going into the base, which is what we want. But at the same time, we can clearly see that we have a big issue here. So maybe I can do the max scale thing again. This does not look like a triangle. It looks like an army of sharks, I guess. So the question is, what is going on here? Well, it's actually very simple. So obviously, as we saw before, our input signal is way too loud, right? So we saw earlier that whenever the swing is too big, then this kind of exponential behavior of the transistor kind of takes over, and it like severely distorts our signal. Now on the plus side, what we can see is that we are actually exceeding, no, we're not exceeding, we're close to reaching our goal of wanting to have a 10 volts peak-to-peak output signal. So we go from 100 millivolts to nearly 10 volts. So it's almost reached, but of course this amount of distortion is of course unacceptable. So the question would be, what can we do about that? Well, answer is very simple. We need to reduce the volume of the signal. So as I said, we have 100 millivolts peak to peak here, and it's obviously way too much to be undistorted by our transistor. So what we need to do is we need to divide it down. And this is kind of where it gets interesting, because I'm unsure actually how much the values we choose for this voltage divider will influence the action of the amplifier. But let's go big for now. So let's go with 100K here, and let's go with a, maybe 1K is actually sufficient, or maybe it works. Let's see what kind of voltage swing we get. So here we get, it's in the microvolts. This might actually be a bit too extreme. So if we pick a 10K here, then we are swinging 2 millivolts peak to peak. I think we can actually go a bit harder here. So if we choose a 20K, going 3 millivolts peak to peak, and probably this is acceptable from a distortion standpoint. You can see it's a little bit rounded, but again, this is a decision you have to make. Like if we drop it down again, probably we should see, it still looks distorted to me. Interesting. Let's drop it down even more and see what happens. Oh, it actually gets more distorted. Isn't this kind of looks low pass filtered, right? Interesting. Didn't expect that. Okay, so maybe this is where these resistor values kind of factor in. Because, I mean, of course, like this capacitor in conjunction with this resistor forms a low-pass filter, right? A high-pass, no, it's a high-pass filter. Wait, then which one is the low-pass filter? Why do we low-pass filter the signal? This is really weird. Let me check the chat. Okay, I will check the comments again. So we have Acer33 saying, what I meant is that you use diodes to rectify input voltage, and I have problem that I want to use DC on input side of a PSU. You can do that with my design. If you use a DC on the input side, you have to use AC to use my design. For DC, I'm not an expert. I think there are converters and there are circuits that kind of do that, but that's a different thing. So you would have to Google that, I'm afraid. So what else do we have? What else do we have? Any questions? Army of Sharks is a good band name. Yeah, probably. Shark suits. That's a good idea. Are you an electrical engineer? I am not. I am just an idiot like all of you. No, I guess more of you are electrical engineers. So No, I'm just a guy who likes to sit in his room and play around with stuff and figure stuff out. That's what I do. Okay, add negative feedback that might fix the rounding. Yeah, we can try that in a second, but I'm unsure if it's actually, if there's some low pass filtering going on. Maybe I'm just hallucinating. Pete says you should check that the current through the biasing resistors is approximately 10 times the base current. I will check that in a second. For a low high pass filter, does it matter on which side the connection to ground is? Oh, my brain is kind of mush. I mean, the thing is, like, if you feed the signal first through a capacitor, and then after that there's a resistor to ground, this is a high pass filter. If the signal goes through a resistor first, and then there's a capacitor to ground, then you have a low pass filter. That's how you differentiate them. But in our case, there's so much going on that it's probably hard to isolate what's happening. Phobos says, I think the cutoff frequency is around 30 hertz with the current. Yes, of course. And our signal is just 40 hertz, which is very low. So what we should probably do to get like a more realistic thing is we need to increase this. We need to increase the scale here. Whoops, we need to severely limit the speed. Okay, and as you can see now, the signal is not affected by this. Okay. Let's turn on the speed a little bit more. Okay, so again, if we pass more of the signal into our resistor transistor, let's see when we actually do get distortion. So here we don't get distortion, so let's do 68K. Actually, it doesn't increase anymore. That's interesting. Let's do 100K. No. Let's delete this guy. Okay, this is interesting. I mean, probably it's that you have like some weird voltage divider, you know, just by the combination of all these parts. That's what I would assume here. Let's try to take this guy out again, put him in here, see what happens. Okay, now we get our exponential distortion again. So we definitely need the voltage divider. I do believe that maybe this resistance here, in conjunction with the stuff that's happening here behind the capacitor, is probably influencing the swing at this point, right? So where are we swinging right now? We are swinging between, let me put in an output. Boom. Let me show the voltage. No, show me the voltage, come on. Boom. Okay, so now we have a swing between -1 and nearly 5 millivolts. Interesting. It's also interesting that it's, no, it's not interesting that it's off center, because of course you have the biasing voltage here. So all this stuff influences each other. So it's not as clean cut. So you can't look at it. You can't look at it isolated. Okay, so let's turn up the speed, and let's turn on the negative peak value again. Okay, and now we can kind of try to estimate like where we stand in relation to our goal. So we wanted to have a 10 volts peak to peak signal. We are now at 6.23, and here we are at 4.71. So that's not even 2 volts peak to peak. So there's a lot left to be desired here. Okay, so now the question is, can we apply what we just learned about the gain? So can we increase the gain? And my idea was basically that we increase the resistance at this point. So let's go really far for now. Let's do a 33K. And now we can see that we are running into we're running nearly into the ground rail, which is not good. So what we would need to do but this is unfortunate because, I mean, now what I would want to do is I would want to decrease the biasing current so that the wave kind of slides upwards. But at the same time, this will decrease the gain, I'm pretty sure. But, I mean, let's try it. Let's bump this up to 5K5, maybe. Ah, that's the wrong direction. So we have to go down. Right? Ah. Okay, so at 5K, we now have a voltage swing of between 4.6 volts and 2.5. So we gained a little bit. So now we're at around 2.1 volts peak to peak. Okay. So this does not look that bad. Maybe we can try to reduce the resistance here a little bit and see if that introduces distortion. Well, I would say it's still kind of acceptable. Okay, so now we have 5 volts and 2.2 volts, about 3 volts peak to peak. This is still very far off. Okay, so what I maybe try to do is I will increase the voltage here, and that sends this thing crashing into the ground rail again. So I guess we need to decrease the voltage here again, just a tiny bit. Okay. I'm not sure if we won much. Now we're between, no, we did. We're now between 4.7 and 1.4. So this is 3.2 volts. We just won like a tiny little bit. Well, let's go really extreme. Let's go 100K. And then we need to drop down to maybe 4K5. I think we need to adjust this more finely to really like get everything out of this thing. Oh, this is still not right. Yeah, this is where it crashes. Okay, 4K7. Okay, now we have 4 volts peak to peak. Okay, this is still pretty disappointing, and we got a lot of distortion. Let me check the chat if anyone has an idea. Like, please, if you know how to really boost the gain here, and I know it should be possible, then please put that in the chat. Wait, I have to turn on my lights. It's getting really dark in here. Oof. Okay. So, let me check the chat. For scaling down, I use the potentiometer, and the higher the value of the potentiometer is, the less shark effect I have. The higher the value of the potentiometer, yeah, that means that you have less current going in. That is going to have an effect, definitely. You can switch the portion of the cape and series resistor, so that should be voltage. I think it would be fun to make a mystery distortion where you can put a ton of components in a Eurorack module and play around with it. Yeah, that sounds fun. I think you're outside the linear region of the transistor. Yeah, I definitely am. That's where you see the rounding effect. But still, I actually think it should be doable like this. I mean, of course, you're right. Like I would need to drop this down because it's already rounding. But I think if I remember right, then if I open up a new one here, I think that they actually have like an example circuit here. Wait, let me see if you can see this. Oh yeah, you can. Cool. I think they have an example circuit in here, which is just, a common emitter amplifier, right? And right, so they have, what do they have here? Show negative peak value. So they have nearly what we're looking for. They have nearly 10 volts peak to peak, and they're coming from a 500 millivolts signal. Okay, and now let's kind of check what they do differently. Well, first of all, they have way more supply voltage. They have 20 volts here. But other than that, it looks like they are doing exactly the same thing that we are doing, except for the emitter resistor that they add. So let's try and drop this thing here down, see what that does. And as expected, that has an effect on the gain. So now we're at -6 to 2, which is still 8 volts, which is still impressive. Now the question is, why are they so much better than me? Well, probably because the input signal is louder, right? They have 500 millivolts. That is probably going to be a factor. But still, like, why is this not distorted? That would be my question. This should be distorted, right? It's probably because of the emitter resistor. So okay, let's do what you told me to do, like for the better part of like an hour, and then put in an emitter resistor. So we put in a 1K resistor here, and we try to see what happens. Like I was hesitant to do this because I know that this is going to actually reduce the gain. So if you put a resistor here, like I said earlier, it kind of acts as negative feedback, and it will kind of make the transistor more linear, but also less gainy, for lack of a better word. I'm sorry. Okay, but I think what we can now do is we can like really drop down the resistor here, so we can apply more of the input signal to our transistor. And I think maybe we can just drop the resistor at all. No, actually, this is very distorted. So we do need a resistor here. 1K is not enough. 10K should probably get us somewhere. Yes. Okay, so let's just try to copy their values. So what they had here, I think, was 110K, and what they had here was 10K. And then what they were using here, I think, was also 10K, right? Okay, but we actually don't get the same kind of results. We get just 1 volt peak to peak. Not even 1 volt. Let me check one last time. And I think after that I'm actually done for the day. So I will actually leave you. And we weren't even able to get like a proper common emitter going. So that's very sad, but that's how life is sometimes. Okay, so they have the same values here. They have the 10K, they have the 1K. Did they? No, they have also the 100 gain. Of course, this is way louder, and I still don't understand why this doesn't distort. But I mean, they made this program. Maybe they cheated. So let's just try to copy this one last time. So you just feed the oscillation straight in here. We have 110. We have 10K, 1K. And we have a measly 1 volt peak to peak. Okay, and now if we raise this up as much as they did, then we get a rounded peak. And we get close to 10 volts peak to peak. But I mean, this is kind of stupid, because now the input signal is so loud, and we said we wanted to use the 50 millivolts. But yeah, maybe we would just need to use multi-stage. So, amplify the amplified signal again. Probably. Yeah, I think I'm going to leave it at that. So I'm going to go back to the chat one last time, and we can look at some questions again. And if you don't have any anymore, I think I would like to end it here, because I'm pretty done. Like I said, I will do like in the video on the VCA, on the transistor VCA, I will kind of condense all the stuff that we have today. I will do more research to kind of iron out like all the stuff that now we didn't get to work properly, and I will try to put all of this in this proper video. So yes, questions, please ask me questions. I will look at the stuff that you have here. Which is, first of all, someone said multi-stage multiple times, and yeah, that's true. Like I said, I think we would need to amplify the amplified signal again. If that's what you mean, correct me if I'm wrong. I think that's what you mean, but yes, that way we could definitely probably get our signal up. But I'm just thinking that wouldn't that also introduce distortion again? Ugh, my head is mush, I can tell you. Okay, further questions. Choose the quiescent current first, then calculate collector resistor to get the 6 volts, then calculate bias current with beta, and finally calculate the biasing voltage divider. Probably this is how I should do it, and probably this is how I kind of opt to not use transistors so much, because if I had to do the same thing with an op amp, it would just be like dirt simple. It's just a few resistors and bam, you're done. But yeah, so let's go on. You need an emitter resistor. I tried to do that, didn't do so much. Philip Miller says emitter resistor increase linearity but decreases again. Yeah, that's what I said. I think that's the trade-off that you make there. Larger cap. Larger cap has lower cutoff frequency. True. Christian, how does the Felsted shape look if the input is a triangle? I think I tried it in their version, and you saw that the tip was kind of rounded, so they cheat. Dirty cheaters. Do not need more stages if correctly biased. Yeah, probably. It's probably just about the biasing and the correctly set quiescent point and all this stuff. And yeah, you would probably need to calculate this. Maybe like if I sat on this computer for 5 more hours and just tried around, probably we could get somewhere. But like I said, I'm too mushy to do that, and I think it wouldn't be so fun. So yeah, probably this is where actually you have to start using some maths and calculate some stuff. So yeah, this might be the limit for me. Blubber Boop says, how do you multistage if you then need to scale down the input signal again for the transistor-based? That's actually also what my point would be, because yeah, you would need to scale it down to not get distortion, and that's a problem. So that probably doesn't work. So ID3M asks, will your VCO circuit work with different Schmidt trigger inverter? It really depends. The problem is that there's a bunch of other chips that are labeled Schmidt trigger inverters. The problem is that most of them are limited to 5 volts supply voltage. So they will die if you feed them any more than 5 volts. And so the chip that I use can handle up to 20 volts, I think. And that's why it works like in my 12 volt system. So yeah, I mean, you could adapt the circuit to work with a 5 volts maximum Schmidt trigger inverter. You would have to use a separate 5 volts rail, but that's why I chose not to use that. And that's why I always tell people, hey, just get the 4106 because it's suited for that application. Okay, QP says, very good, thank you. You did well. This hard topic, yeah, it's very hard. Thank you. I appreciate the warm words. So the random German guy says they also had 1 mega ohm to ground on the output. Yeah, that's just they had AC coupling on the output, but I don't think that really does much. So Pete says if you increase the biasing resistors, the input resistance can be increased, and this should increase the gain to an extent. Probably, but like I said, I'm too tired. Next time. Philip says Ohm's law rules. Yeah, I mean there's not really a choice, so you can't go without it. So probably true. ID3M says this one has smaller hysteresis gate opening. Like I said, I think the main thing is actually the supply voltage. If you can handle that, if it can, of course, then it probably can work. But I would say just try it. Okay, guys, so if there's nothing else, then I would end it here. As always, I will put the stream as a replay on my Patreon. And just to say it again, I will condense this into the next episode, and you will get a condensed version of this with less stuttering, less planless, aimless wandering, and less failure, I hope. So I hope you can look forward to that. And thank you guys very much for watching. And I will see you in the next stream, probably. I think I want to make another one next week. I won't do it on transistors because they warp my brain, so this will be in the future. And I just see that there's more messages coming in. Let me read them quickly. So Atenus says, instead of CD4106, why not use TLO74 with -2 ground? You can do that. I chose not to do that again because I tried to be as accessible as possible. And to my mind, it is much easier to explain how a 4106 Schmitt trigger works than the op-amp configured as a Schmitt trigger. You know, just because it's more concepts to worry about. But functionally, you're right. You can use an op-amp, and probably you can make the circuit simpler because you can just use op-amps. You don't have to use additional chips. So yeah, it's something that you can do. Okay. More questions. Higher cap with no input resistance is still infinitely better. RC constant wise than cap and res, or am I wrong? Yes, the ESR is higher, but many times better. Probably. I can't really engage with that at the moment, but yeah, I think you might be right. Okay. Any more questions? A cap on the emitter parallel to the 1K will also increase AC gain. Yeah, I guess. But that's, like I said, that's something for next time. So thank you again. Thank you all for watching. And I will see you in the next stream next weekend, or if you can't make it there, then in the next video. So have a good night, guys. Talk to you soon. Bye-bye.